Imagine a world where there is no dry land, no mountains, no beaches, no continents, just water in every direction, covering the entire planet like an endless ocean. For a long time, scientists thought planets like this only existed in our imagination, but it turns out they are out there, orbiting distant stars, trillions of kilometers away from us. These water worlds hold secrets that could change everything we know about life in the universe. Could there be something waiting to be discovered beneath those deep waters? Get ready to fall asleep while listening to this video. Subscribe to the channel. Leave your like and comment where in the world you are watching from. Get comfortable and relax. Let us begin. Imagine a world with no mountains, no deserts, no forests, just an unbroken expanse of water stretching from pole to pole in every direction. How does such a planet not only form but endure for eons without a single speck of dry land ever breaking its surface? The genesis of a true water world begins in the chaotic aftermath of a star's birth, within the swirling protoplanetary disk of gas and dust. For a planet to end up entirely cloaked in ocean, it must coalesce within the star's habitable zone, that Goldilocks region where temperatures allow liquid water to exist, but with a crucial twist. Its formation history must lack the specific conditions that lead to the rise of continents. This isn't just about having enough water, it's about a planetary architecture that actively suppresses land emergence. The initial composition of the building blocks is key. If the planet forms from material that is overwhelmingly rich in icy compounds and poor in the heavier rocky elements that form buoyant continental crust, the stage is set for a global ocean. The delicate balance of forces during planetary accretion is another piece of the puzzle. On Earth, the relentless churn of plate tectonics constantly recycles crust, pushing up mountain ranges and new land. But on a water world, this tectonic engine might be stillborn or operate in a fundamentally different way. Perhaps the planet's internal heat flow is too low to drive vigorous plate movements. Or maybe the constant presence of a massive water layer lubricates the crust so thoroughly that it slides as single, unbroken plates, preventing the subduction and crumpling that builds continents. The stability of such a world is a profound geological mystery. It requires a perfect, long-term equilibrium between the heat radiating from the planet's core, the gravitational interactions with its star and any moons, and the insulating effect of the ocean itself. A slight shift in any of these factors could, over millions of years, either evaporate the ocean into space or lock it into a global ice shell. The sheer volume of water is staggering. We are not talking about an ocean a few kilometers deep like Earth's. We are discussing a layer that could be hundreds of kilometers thick. This immense column of water creates pressures at the bottom that are almost beyond comprehension. At those depths, water is no longer a simple liquid. It undergoes phase transitions, turning into exotic forms of ice like Ice 6 or Ice 7, which remain solid even at high temperatures because the pressure is so immense. This creates a bizarre internal structure, a deep liquid ocean, then a layer of hot, solid ice, and finally the actual rocky sea floor, which might never directly interact with the liquid ocean above. This high-pressure ice layer could act as a lid, sealing off the rocky interior and its potential nutrients from the ocean above, which has huge implications for the possibility of life. The absence of land also dismantles a key climate regulator we take for granted on Earth, the silicate carbonate cycle. On our planet, rainfall weathers silicate rocks on continents, drawing carbon dioxide out of the atmosphere. The carbon is eventually transported to the ocean floor and subducted back into the mantle, releasing the gas through volcanoes in a beautiful, self-regulating thermostat. A water world has no silicate rocks exposed to the atmosphere. Without this cycle, how does the planet avoid a runaway greenhouse effect or a global snowball state? The climate must be stabilized by other means, perhaps through the ocean's own massive heat capacity and its circulation patterns, or through biological activity if life exists. The source of all this water is another fundamental question. Did the water form alongside the planet? As a native component of the original planetesimals that collided to build it? If those building blocks were similar to the icy comets and asteroids in our outer solar system, then the planet was born wet. Alternatively, the water could have been delivered later in a violent period known as the Late Heavy Bombardment, where a rain of icy comets pummeled the young planet, depositing their water onto its surface. The answer lies in the subtle chemical fingerprints of the water, like the ratio of deuterium to normal hydrogen, point, which could tell us if its origin is local or foreign. Understanding these worlds isn't just a theoretical exercise. With telescopes like James Webb, we are now identifying exoplanets with densities so low they must be composed largely of water. These real-world examples are proving that ocean planets are not just science fiction, but a tangible, and perhaps common, class of world in our galaxy. Their very existence challenges our Earth-centric views of planet formation and forces us to reconsider the basic ingredients and processes that create a stable, lasting world. The genesis of an ocean world is a story written in water, a narrative of cosmic chance and delicate balances that creates an environment both profoundly alien and hauntingly familiar. Every aspect of its formation, from the first grains of dust to the final delivery of its life-giving water, conspires to create a sphere of perfect blue, a testament to the diverse outcomes of planetary birth. The stability of such a place is not a given. It is a continuous dance of physics and chemistry, a precarious existence that, for some worlds, can last for billions of years, offering a potential cradle for life in the vast, dark ocean. But beneath that serene blue surface lies a realm of unimaginable extremes, where the very nature of water itself is twisted into alien forms. Descending into this abyss is a journey into a world defined by crushing pressure, eternal darkness, and physical transformations that challenge everything we know about liquid environments. As we leave the sunlit surface behind, the pressure begins its relentless increase. For every 10 meters you go down, the pressure rises by about 1 atmosphere, but on a planet with an ocean hundreds of kilometers deep, this accumulation becomes astronomical. Long before reaching the midpoint, the pressure would be thousands of times greater than at the bottom of Earth's Mariana Trench. At these depths, water is no longer the familiar fluid that flows and splashes. It undergoes dramatic phase changes. Due to the immense weight of the water above, the molecules are forced into crystalline structures, forming types of ice that are hot, not cold. This is where we encounter exotic states like Ice 6 and Ice 7, which remain solid even at temperatures that would boil water on the surface because the pressure prevents them from melting. These ices are denser than liquid water and would form vast, hot ice layers within the ocean, creating a bizarre internal geography that is nothing like the rocky seafloors of Earth. The darkness that envelops this realm is absolute and perpetual. Beyond the first kilometre, sunlight is completely extinguished, leaving a blackness deeper than any cave on Earth. This is not just the absence of light, it is a profound void where vision is useless, and any exploration would rely entirely on other senses like sonar or touch. The crushing pressure affects not only water but any potential object or life form, for creatures or machines. The force would be equivalent to having multiple elephants balanced on a postage stamp across every inch of their surface. Any hollow structure, any gas-filled cavity would be instantly imploded into oblivion. This makes the very idea of buoyancy or swimming with air bladders completely impossible, posing a fundamental barrier for life forms that rely on such adaptations. The zone where water transitions into these high-pressure ices is often called the compression zone, a boundary layer where the physical properties of the medium change drastically. This zone could act as a formidable barrier, segregating the upper ocean from the lower layers. For any biology based on Earth-like principles, this transition might be insurmountable. Enzymes and cellular structures that function beautifully at surface pressures would be distorted and denatured under such force. The biochemical processes that support life would need to be radically different, perhaps relying on stronger molecular bonds or existing entirely within the solid but hot ice matrices. The concept of a seafloor itself is redefined here. Instead of a rocky bottom, there might be a global layer of hot, solid ice, a crust of ice 7 or other phases that forms the actual foundation of the ocean. This ice layer would be dynamically interacting with the planet's interior, possibly with geothermal heat slowly melting the base and creating a complex interplay of phase changes. In some regions, where the geothermal heat flow is high, there might be pockets of liquid water trapped between layers of ice, creating isolated environments that could harbour unique ecosystems. The pressure at this ultimate depth is so extreme that it approaches the limits of what matter can withstand, potentially compressing water into even stranger states like supersonic ice, where oxygen atoms form a lattice and hydrogen ions flow through it like a metal. Exploring these depths with technology is a nightmare of engineering. A submarine designed for this environment would need to be a perfect sphere, the shape best suited to distribute pressure evenly, made from materials like titanium alloys or advanced ceramics that can resist deformation. But even the strongest human-made materials would struggle at these depths. We might need entirely new substances or active support systems that we have not yet invented. Powering such a vehicle is another colossal challenge. Solar panels are useless in the darkness, and batteries would need to last for years without recharging. Nuclear power sources, like radioisotope thermoelectric generators, become a necessity, but they must be miniaturized and shielded to operate under such conditions. Communication with the surface or an orbiting mothership is nearly impossible. Radio waves are absorbed quickly in water, so data transmission would require acoustic modems using sound waves. But even sound travels differently under extreme pressure, with signals becoming distorted over long distances. The vehicle would need to be fully autonomous, making its own decisions in real time because the communication delay to any external controller could be hours or days, making remote control impractical. The journey down would be slow and cautious, with the submersible equalizing pressure internally as it descends to avoid catastrophic failure. Every instrument, every camera, every sensor would need to be specially designed to function under these conditions. Cameras would require their own pressure-resistant housings and advanced lighting systems, but light itself would be absorbed quickly in the dense, particle-rich water, limiting visibility to just a few meters even with powerful lamps. Sampling the environment would be incredibly difficult. Any mechanical arm or drill would need to operate with immense strength to overcome the pressure, yet with fine precision to collect samples without contaminating them. The heat generated by the vehicle's systems would be a constant concern, as it could alter the local environment or melt the surrounding ice, potentially triggering unstable phase changes. Bringing samples back to the surface for study is another Herculean task. They would need to be kept at the same pressure and temperature throughout the ascent to prevent them from decomposing or exploding. The psychological aspect for any hypothetical crew would be daunting, trapped in a tiny sphere, surrounded by utter blackness and knowing that any leak would mean instant death, requiring immense mental fortitude for robotic missions. The autonomy software would need to be exceptionally robust, capable of handling unexpected obstacles like sudden currents, ice formations, or geological activity. The potential for discovering life in this abyss is a driving force for such exploration, but the forms it might take are beyond our current imagination. Organisms here could be slow-moving, with gelatinous bodies that have no gas spaces, their metabolisms tuned to the slow release of geothermal energy or chemical reactions from vents. They might use bioluminescence for communication, but in the eternal darkness, even that might be scarce. The food web would be based on chemosynthesis, similar to Earth's hydrothermal vents, where bacteria convert chemicals like hydrogen sulfide or methane into energy, but the pressure could allow for novel biochemistry, such as enzymes that function better under compression, or lipids that form more stable membranes. The isolation of different layers by the compression zone could lead to entirely independent evolutionary paths, with species in the upper ocean never encountering those in the lower liquid layers or within the ice matrix. The search for life must account for these possibilities, looking not just for DNA-based organisms, but for alternative biochemistries that thrive under pressure. The darkness is not just a lack of light. It influences behavior, reproduction, and social structures. Without light, mating rituals might involve sound, vibration, or electrical signals. Predators might rely on sensing minute pressure changes or the disturbances in water caused by movement. The sheer scale of this environment means that ecosystems could be vast yet disconnected, with species adapted to specific pressure bands or chemical niches. The abyssal plains on the ice crust could be home to fields of strange, slow-growing organisms that feed on the constant rain of organic detritus from above, if any surface life exists. Alternatively, life might be concentrated around hydrothermal vents on the ice crust, where geothermal heat creates oases of liquid water and rich chemical soups. These vents would be under immense pressure, spewing superheated water that is prevented from boiling by the weight above, potentially creating unique mineral formations and energy sources. The study of these depths not only helps us understand alien worlds, but also pushes the boundaries of physics and biology on Earth, informing our search for life in the oceans of moons like Europa or Enceladus. The challenges of exploring this inhospitable abyss are monumental, but the rewards could be revolutionary, revealing new states of matter, novel forms of life, and a deeper understanding of how planets function. As we contemplate sending probes into these darknesses, we must innovate relentlessly, developing technology that can withstand what seems unimaginable, all to answer fundamental questions about existence in the most extreme environments the universe has to offer. While the abyssal depths present a static world of immense pressure and eternal night, the ocean above is anything but still. It is a dynamic, pulsating entity defined by its currents. On a planet with no continents to act as barriers, these currents are the true geographical features, the rivers and highways of a world without roads. They are the architects of climate, the distributors of heat, and the potential carriers of life across the globe. The wind, blowing unimpeded over an endless surface, transfers its energy directly into the water, generating currents that flow in vast, unbroken loops. These are not the disrupted, continent-channeled flows of Earth. These are planetary streams that can circumnavigate the globe, building momentum over thousands of miles without a single shoreline to dissipate their energy. The primary engine of this global circulation is the thermohaline system, a massive conveyor belt driven by differences in temperature and salinity. In the sun-warmed equatorial regions, water heats up and becomes less dense, spreading towards the colder poles. At the poles, this water releases its heat into the atmosphere, cools dramatically, and often freezes at the surface, a process that leaves behind salt-rich, incredibly dense brine. This cold, salty water sinks, plunging into the abyss and initiating a deep, slow return flow back towards the equator. This continuous overturning is the planet's heart and lungs, pumping heat from the equator to the poles and ensuring a stable climate over geological timescales. Without land to interrupt this flow, the thermohaline circulation could be a single, continuous loop, a global current of immense power and consistency. The patterns that emerge from this system are on a scale we can hardly imagine. Permanent megawhirls, oceanic gyres hundreds of times larger than any on Earth, could spin for millennia, acting as massive, isolated marine provinces, planet-girdling currents, like a single unified Antarctic circumpolar current, but with no land to constrain it, would race around the world, its speed limited only by the friction of the water itself. These currents dictate everything. They determine where the warm water pools, creating stable, tropical-like zones even at high latitudes, and where the cold upwelling from the depths brings nutrients to the surface. The distribution of life, from the microscopic phytoplankton to the largest predators, would be entirely at the mercy of these flows. Nutrients from the deep, whether from geothermal vents or the slow rain of organic debris, would be swept up by these currents and carried across the planet, fertilizing vast stretches of the surface ocean and supporting complex food webs. The interaction between the ocean and the atmosphere is far more intimate and powerful than on Earth. With no land to break up weather systems, the evaporation from the vast ocean surface fuels the atmosphere with immense amounts of moisture and heat. This can lead to storm systems of legendary proportions. Hurricanes, or their alien equivalents, could form and travel for years, even centuries, continuously gathering energy from the warm ocean below. They would not make landfall and dissipate. They would wander the globe, growing in size and intensity until they eventually encountered a region of cooler water that finally robbed them of their power. The waves generated by such persistent winds would be monumental, not mere swells, but travelling hills of water that could theoretically reach heights of hundreds of metres, though the sheer scale of the ocean might make them appear as gentle rolling giants from a distance. The climate itself is a direct product of this ocean-atmosphere coupling. The ocean's incredible heat capacity acts as a global thermostat, absorbing heat during periods of increased solar radiation and releasing it slowly during cooler times, preventing the wild temperature swings that would characterize a rocky planet. The dense, water vapor-rich atmosphere, a powerful greenhouse blanket, works in tandem with the ocean to trap heat, ensuring the surface remains largely ice-free except perhaps at the very poles. However, this stability is not absolute. Small changes in the planet's orbit or solar output could trigger feedback loops. A slight cooling could increase ice formation at the poles, raising the planet's albedo and reflecting more sunlight, potentially leading to a runaway global glaciation, a snowball world where even the equator freezes over. Conversely, a slight warming could increase evaporation, putting more water vapor, a potent greenhouse gas, into the atmosphere, accelerating the heating in a runaway greenhouse effect that could ultimately boil the ocean away into space. The study of these current patterns is not just academic. It is essential for understanding the planet's habitability and for any future exploration, for a potential robotic submarine. Navigating these currents would be a monumental challenge. Sailing through a current flowing at dozens of knots would be like trying to swim up a waterfall, requiring immense power and energy reserves. Conversely, a clever explorer could ride these currents like interstellar highways, using them to traverse the globe with minimal energy expenditure. The currents also define the sensory environment for any life. In the sunlit zone, organisms would drift with the flows, part of a global planktonic community constantly circulating. In the darkness below, the slow, deep currents would carry chemical signals and nutrients, potentially allowing for communication or migration across vast distances. The soundscape of the ocean would be dominated by the noise of these moving water masses, the groaning of massive bodies of water sliding past one another, the roar of deep currents scouring the hypothetical ice seabed, and the constant rush of fluid in motion. For intelligent life to evolve here, an understanding of these currents would be as fundamental as our understanding of fire or the wheel. Their migration routes, their hunting grounds, and their social networks would be mapped onto these invisible highways in the water, predicting the shifts in current patterns, which might signal the change of seasons or the arrival of nutrient-rich upwellings, would be a matter of survival. The climate of a water world is thus a symphony conducted by gravity, rotation, and solar heat, played out on an instrument of pure liquid. It is a system of beautiful complexity and terrifying power, where the only constants are flow and change, a perpetual dance that shapes every aspect of existence from the surface to the abyss. Understanding this dance is key to unlocking the secrets of whether such a world could ever be a home for life as we know it, or for forms of life we have yet to imagine. The currents are the planet's pulse, and by listening to that rhythm, we can begin to comprehend the life of a world that is nothing but ocean. But if those currents are the planet's circulatory system, then the search for life is the quest to find its pulse, to detect the subtle chemical whispers that biology leaves behind in the water and the air above it, on a world covered entirely by ocean. The first and most detectable signs of life might not be visible creatures but atmospheric anomalies, specific combinations of gases that should not exist together without a continuous biological source replenishing them. Imagine a telescope analysing the light filtering through this world's atmosphere and finding oxygen and methane coexisting in significant quantities. On a sterile, abiotic planet, these two gases would quickly react with each other and disappear. Their persistent presence is a massive red flag for life, a biosignature screaming that something is constantly producing them. This is because life, in its metabolic processes, creates chemical disequilibrium, pushing the atmosphere away from a state of stable boredom and into a dynamic, unstable mix that hints at the frenzy of activity below the waves. But life on a water world would not be limited to the sun-drenched surface. In the perpetual darkness of the deep ocean, where sunlight is a forgotten myth, entire ecosystems could thrive completely independent of photosynthesis, drawing their energy from the planet's internal heat, around hydrothermal vents on the seafloor, or perhaps on the hot ice crust itself. Superheated water rich in dissolved minerals like hydrogen sulfide and methane would spew into the cold depths. Here, microbes analogous to those on Earth could perform chemosynthesis, using the chemical energy from these compounds to power their metabolism, building organic molecules from scratch without a single photon of light. These chemosynthetic oases would form the base of a food web that could support a menagerie of strange organisms, from filter-feeding creatures anchored to the rock or ice to free-swimming predators, all flourishing in the absolute dark under immense pressure. The very chemistry of the ocean itself would be the ultimate dictator of what form life could take. the water's salinity, its pH level, and the abundance of key elements like sulfur, iron, phosphorus, and nitrogen would set the rules for the biochemical playground. In a slightly acidic ocean, life might evolve to use different molecular structures for its cells, perhaps relying on sturdier lipid membranes. If sulfur is plentiful, biological processes might incorporate it into fundamental cycles, much like the sulfur bacteria found in Earth's own deep-sea vents. The presence or absence of certain trace metals could determine which enzymes are viable, steering evolution down one biochemical path versus another. For any potential explorer, whether a remote telescope or a future submarine, the hunt for these biological clues would focus on the water column. The detection of complex organic molecules like lipids or amino acids floating freely would be a tantalizing hint, but not conclusive proof, as some can form through non-biological processes. A much stronger indicator would be the discovery of biological pigments. In the sunlit surface waters, organisms would almost certainly evolve to harvest solar energy, and they would need pigments like chlorophyll to do it. A spectral analysis of the surface ocean revealing a distinct absorption signature of alien chlorophyll or a similar photosynthetic molecule would be revolutionary. Even in the twilight and dark zones, the search for pigments wouldn't stop. Life there might use pigments for purposes other than photosynthesis, perhaps for camouflage, UV protection, or as part of a sensing mechanism. Furthermore, the constant drizzle of organic material from the upper ocean, the marine snow, would be a critical lifeline for the deep, dark communities. This slow, endless rain of dead cells, fecal matter, and other biological debris would carry energy from the photic zone down into the abyss, potentially sustaining filter feeders and scavengers in the layers of permanent night. This vertical connection means that life on a water world could exist in a vast, interconnected column, with each depth zone hosting its own specialized organisms adapted to the specific conditions of pressure, temperature, and light availability. The surface zone would be a bustling metropolis of photosynthetic activity, with planktonic organisms drifting in the currents, possibly forming vast, visible blooms that could even be seen from space. These surface dwellers would have adaptations for buoyancy, to stay within the reach of sunlight, and they would be the primary producers, fixing carbon and generating oxygen for the entire planet. Just below, in the mesopelagic or twilight zone, light fades to nothing, and life would transition. Here, bioluminescence could be the dominant form of communication, used for attracting mates, luring prey, or confusing predators in the dim blue glow. The creatures in this zone might undertake daily vertical migrations, travelling hundreds of meters up to feed at night and descending to hide in the darkness during the day. As we go deeper into the aphotic zone, where no light penetrates, life becomes more sparse and specialized, reliant entirely on the chemosynthetic energy from below or the organic rain from above. The immense pressure and cold temperatures would favor slow, efficient metabolisms, with organisms that might live for centuries, growing very slowly in the resource-scarce environment. The possibility of life existing within the hypothetical layer of high-pressure ice is perhaps the most speculative but fascinating, in the tiny channels and pores between ice crystals, where liquid water might persist. Exotic microbial life could eke out an existence, using chemical gradients at the interface between rock, ice, and water for energy. The methods for detecting this life are as varied as the environments themselves. For a distant observer, the atmospheric biosignatures are the first clue. Beyond oxygen and methane, they might look for nitrous oxide, dimethyl sulfide, or other complex gases that are typically byproducts of biological activity. The seasonal variation in these gases could also be a telltale sign, as biological activity often pulses with changes in temperature and light. For a probe in the ocean, more direct methods are needed. Sophisticated sensors could analyze water samples for the homochirality of organic molecules. In living systems, amino acids are almost exclusively left-handed, and sugars are right-handed, while abiotic processes produce a racemic, or equal, mix. This molecular preference would be a very strong indicator of life. Other instruments could look for patterns in the complexity of organic compounds, seeking the unmistakable signature of biological organization rather than random chemical synthesis. The challenge, of course, is contamination. Any probe from Earth must be impeccably sterile to avoid seeding the alien ocean with our own microbes and completely confounding the search. If life is found, the next step is understanding its biochemistry. Is it based on DNA and RNA? Or does it use a completely different information storage system? Does it use the same 20 amino acids we do, or an entirely novel set? The answers would redefine our understanding of life itself. The water chemistry plays such a fundamental role that it could create isolated pockets of life with radically different biochemistries. One region of the ocean, rich in iron, might host life that uses iron-based enzymes, while another, with high sulfur concentrations, might have organisms that use sulfur in their core metabolic processes. The pH could vary with depth, creating acidic havens for some life forms and alkaline environments for others. The constant global currents would eventually mix these chemical signatures, but localized sources like hydrothermal vents could maintain unique biochemical provinces for long periods. The interplay between the physics of the currents and the chemistry of life is intimate and constant. A current shifting course could cut off a deep-sea vent community from its supply of oxygen-rich water, or it could suddenly deliver a bounty of nutrients to a starving surface bloom. Life on this world would have to be incredibly resilient and adaptable to these changes, or it would have evolved strategies to migrate with the flows. The entire biosphere, from the surface to the abyssal plains, would be a single, vast, interconnected chemical reactor, with life both responding to and influencing the ocean's composition. The detection of life on such a world would be one of the most profound discoveries in human history, telling us that we are not alone and that life is not a fluke of Earth but a fundamental force in the universe. It would open up a new frontier of astrobiology, forcing us to expand our definitions of habitability and life. The chemistry of life on a water world is the story of how matter organizes itself against the odds, using the energy of a star or the heat of a planet to create complexity and order in an endless, dark sea. The discovery that life could potentially thrive in the utter darkness of a global ocean, sustained by chemistry rather than sunlight, fundamentally shatters our Earth-centric view of what makes a planet livable. It forces us to tear up the old textbook definition of the habitable zone and redraw it with a much broader, more imaginative stroke. The classic habitable zone, that Goldilocks ring around a star where temperatures are just right for liquid water to exist on a planetary surface, was always a concept built around a planet like ours, with its mix of land and sea. But a world that is nothing but ocean plays by a completely different set of rules. It's massive. Global sea acts as a gigantic thermal battery and a superb climate stabilizer. Because water has such a high heat capacity, it takes a long time to heat up and a long time to cool down. This means an ocean planet can maintain relatively stable temperatures over a much wider range of distances from its star. A planet that might otherwise swing between boiling and freezing could, thanks to its ocean blanket, find a temperate equilibrium, potentially remaining habitable for billions of years even if it orbits a bit closer to or farther from its star than a rocky world could. This expanded concept of habitability is not just about stellar distance. It is about the planet's internal architecture, specifically the depth and composition of its ocean. The thickness of the water layer is a critical factor that can make or break a world's potential for life. An ocean that is too shallow, perhaps only a few dozen kilometers deep, might be more susceptible to global freezing or complete evaporation if the climate tips too far in one direction. It lacks the thermal mass to buffer against severe changes. Conversely, an ocean that is too deep, stretching down hundreds of kilometers, presents another set of problems. As we discussed with the abyssal pressures, at a certain depth the water transitions into those exotic, hot, high-pressure ices like Ice 6 and Ice 7. This could create a thick, solid layer of ice that forms a permanent lid over the rocky seafloor. This is a devastating prospect for habitability. It would physically isolate the liquid ocean above from the geochemical richness of the planetary mantle. On Earth, the constant chemical exchange between the ocean and the rocky crust through hydrothermal vents and plate tectonics provides a continuous supply of essential nutrients like phosphorus, iron, and sulfur. If a high-pressure ice layer seals off that connection, the ocean above could become a nutrient-poor desert, potentially limiting the abundance and diversity of life. The life that does exist would be entirely dependent on recycling what is already in the water or on atmospheric deposition. So, the sweet spot for a habitable water world might be an ocean deep enough to provide global climate stability, but not so deep that it forms a permanent ice barrier, allowing for some form of communication between the water and the rocky interior. The next fundamental question is the source of energy for any potential biosphere. On Earth, the vast majority of life is ultimately powered by sunlight, captured by photosynthetic organisms at the base of the food web. On a water world, this would certainly be true for the sunlit surface layers. But as we have seen, life could also be powered from below, by the planet's own internal heat, geothermal energy, leaking from the planet's core, could drive chemosynthetic ecosystems at hydrothermal vents on the seafloor, or even on that high-pressure ice crust if it has its own geothermal activity. This duality of energy sources dramatically increases the potential for life. A world orbiting a dim, cool star where surface sunlight is faint and weak might still host a thriving biosphere in its deep, dark oceans, entirely independent of the star's light. This means the habitable zone for a water world is not a single band, but a spectrum of possibilities, depending on which energy source life taps into. For surface life, the traditional habitable zone still applies, but for deep sea life, the concept expands to include worlds much farther from their star, as long as they have enough internal heat to maintain liquid water and active geology. Another often overlooked factor is the planet's magnetic field. A strong global magnetic field, generated by a churning molten core, acts as a shield, deflecting the intense charged particles of the stellar wind. Without this shield, a planet's atmosphere can be gradually stripped away over time by these relentless particle streams. For a water world, this is a double-edged sword. Losing its atmosphere would lead to the eventual loss of the ocean itself, as water vapor in the upper atmosphere would be split by radiation and the hydrogen lost to space. So, a magnetic field might be crucial for long-term habitability, preserving both the atmosphere and the ocean. However, if the ocean is extremely deep, The pressure at the bottom might be so immense that it suppresses volcanic activity and the convection in the core needed to generate a magnetic field, creating a tragic paradox where the very ocean that enables life also prevents the formation of the shield that protects it. This leads us to the concept of layered habitability. A single water world might not be uniformly habitable. Instead, it could be a planet of niches, with different layers of the ocean offering vastly different environments for life. The surface photic zone, bathed in sunlight, could be home to photosynthetic organisms and a complex food web that depends on them. Just below, the twilight zone might host communities of organisms that migrate vertically to feed, using bioluminescence to communicate and hunt. Deeper still, the aphotic zone could be a realm of slow-moving, pressure-adapted life sustained by the constant rain of organic detritus from above. And at the very bottom, whether it is a rocky seafloor or a hot ice crust, chemosynthetic oases around hydrothermal vents could support isolated ecosystems utterly alien to the surface world. These layers might be connected by the global currents we discussed, exchanging nutrients and organisms, or they could be largely isolated from one another by sharp gradients in temperature, pressure, or chemistry, leading to entirely independent evolutionary paths. The search for habitability on such a world is therefore not a simple yes or no question. It is a multidimensional puzzle involving stellar distance, ocean depth, internal heat, magnetic field strength, and atmospheric composition. When we look at candidate exoplanets from afar, we are now learning to look for these subtle signs. A planet with a low density indicates a world rich in water and light elements, a potential water world. Spectroscopy of its atmosphere can reveal the presence of water vapor and potential biosignature gases like oxygen or methane, but it can also hint at the stability of that atmosphere, which relates to the magnetic field. Measurements of the planet's orbit and the star's activity can tell us about the radiation environment. The future of habitability studies lies in modelling these complex, interacting systems to understand which combinations of factors can sustain a liquid ocean and, ultimately, life over geological timescales. This redefined habitable zone is not a narrow, well-defined ring, but a fuzzy, expansive domain filled with possibilities. From steam-bathed worlds close to their stars to ice-covered moons with hidden oceans in the outer reaches of their systems. The water world forces us to think in 3 dimensions, to consider the entire volume of a planet's ocean as a potential habitat, and to accept that the ingredients for life might be stirred not just by the light of a star, but by the slow, persistent heat of a planet's own beating heart. This expanded view makes the universe feel far more generous, suggesting that life could find a way in environments we once thought utterly hostile, as long as there is liquid water, an energy gradient, and a suite of essential elements. Our own solar system provides tantalizing examples of this layered habitability in miniature. The moon Europa, orbiting Jupiter, is a frozen world with a subsurface ocean that may be twice the volume of Earth's oceans, kept liquid by tidal heating. Its potential habitability has nothing to do with the Sun's habitable zone and everything to do with the internal energy provided by its gravitational interactions with Jupiter. Enceladus, a small moon of Saturn, sprays its subsurface ocean into space from geysers at its south pole, and that water is rich in salts and organic molecules, a promising sign for chemosynthetic life. These are water worlds in their own right, just on a smaller scale, and they have taught us that habitability is not a property of a planet's address alone, but of its entire dynamic history and internal structure. As we discover more exoplanets, we will undoubtedly find many that defy our simple categories. Worlds that are mostly ocean with perhaps a few submerged mountain peaks or volcanic islands. These worlds will test our new definitions and force further revisions. The journey to understand habitability is just beginning, and it is leading us to a universe that is far more diverse and wondrous than we ever imagined. A cosmos where the conditions for life may be almost everywhere, waiting in the dark, silent depths of endless oceans. While the hidden depths may cradle the subtle chemistry of life, the surface of this water world is anything but subtle. It is a raging, ever-changing arena where the elements engage in a perpetual dance of immense power. Without a single grain of sand or blade of grass to interrupt the wind's flow, the atmosphere transfers its energy directly into the water with terrifying efficiency, generating waves on a scale we can scarcely comprehend. These are not the waves that crash on a beach and dissipate. These are travelling mountains of water, fluid hills that can theoretically reach heights of hundreds of metres, their crests separated by valleys so vast that from a distance, the ocean might appear merely undulating, but up close, it would be a roiling chaos of liquid peaks and troughs. The wind, blowing over thousands of miles of uninterrupted fetch, has nothing to slow it down, so it can push and pull the water surface for days or weeks on end, building up momentum that results in swells that could cross an entire hemisphere. These waves are the planet's primary method of dissipating atmospheric energy, and their constant motion churns the surface layers, mixing heat and gases into the upper ocean and helping to regulate the global climate. But waves are only one part of the surface story. At the poles, where solar energy is weakest, the ocean surrenders its heat to the frigid air, and a cap of ice begins to form. This is not like the thin sea ice of Earth's Arctic. This could be a dynamic, shifting crust of ice that expands and contracts with the seasons, or in more extreme climatic shifts. It could engulf the entire planet in a global glacier. The formation of ice is a critical climate feedback loop. Bright white ice reflects a tremendous amount of sunlight back into space, a high albedo effect that cools the planet further, potentially triggering a runaway freezing event that could lock the world in a solid ice shell for millions of years. Conversely, during warmer periods, the retreat of ice exposes dark ocean water that absorbs solar heat, accelerating warming and preventing the ice from returning. This delicate balance between ice and water is one of the key regulators of the planet's long-term climate stability. The ice itself would be a world unto itself. Not a static plain, but a fractured, pressure-ridged landscape, constantly on the move, driven by the currents and winds beneath and above it, leads and polynyas, areas of open water within the ice, would serve as vital oases for any surface-dwelling life, allowing for gas exchange and providing patches of sunlight for photosynthetic organisms. The ice could also act as a lid, trapping gases beneath it and altering the chemistry of the surface water, or it could be riddled with briny channels where unique microbial ecosystems thrive in the cold and dark. Beyond the ice, the open ocean is the stage for the planet's most violent weather. The constant evaporation from the warm surface pumps enormous amounts of water vapor and latent heat into the atmosphere, fueling storm systems of legendary proportion and duration. Cyclonic storms, similar to hurricanes but on a planetary scale, could form and wander the globe for years, even centuries, with no land to break them apart. These storms would simply continue to feed on the warm water below, growing in size and intensity until they eventually drifted into a cooler region where they would finally lose their energy source and dissipate. The cloud patterns from such a storm would be visible from space as a vast, spiraling system that could cover an area the size of a terrestrial continent, with wind speeds that might exceed anything recorded on Earth. The interaction between the ocean and atmosphere is far more intimate here than on a world with land. The ocean essentially breathes the atmosphere, with gases like carbon dioxide and oxygen constantly exchanging across the surface interface. This exchange dictates the composition of both the air and the water. A warm ocean can hold less dissolved gas, so it releases carbon dioxide, warming the atmosphere in a greenhouse effect. A cooler ocean absorbs more CO2, cooling the planet. This creates a natural thermostat, but one that can be pushed to extremes. The sheer amount of water vapour in the air makes the atmosphere incredibly dense and a powerful greenhouse gas in its own right, creating a thick, cloudy blanket that further moderates surface temperatures but also contributes to the potential for a runaway greenhouse effect if the planet gets too close to its star. The surface is also where the planet meets the void of space, and it is the primary region for receiving stellar energy. The angle of the sun, the planet's rotation, and its orbital path all create daily and seasonal cycles. But on a water world, these cycles are expressed purely through changes in the water itself, the temperature of the surface layers, the intensity of evaporation, and the patterns of waves and currents. For any hypothetical observer, the surface would be a mesmerizing and terrifying sight. Under a clear sky, the sun would glint off an infinite expanse of blue, broken only by the rolling swells. During a storm, the view would be a monochrome grey fury of water and spray, with visibility reduced to near zero. At night, if the clouds parted, the stars would be reflected in a black, heaving mirror, a dizzying perspective of being adrift in both sea and sky. The sound would be a constant, overwhelming roar of wind and water, a white noise that never ceases. For any life forms adapted to this environment, survival would mean mastering this dynamism. Surface-dwelling organisms would need to be incredibly resilient, able to withstand being tossed by colossal waves and to endure the battering of endless storms. They might have streamlined bodies to reduce drag, or they might be largely gelatinous to absorb impacts. Flight, or rather gliding on the powerful winds, could be a common adaptation, allowing creatures to travel vast distances above the waves. The surface might also be home to vast, floating ecosystems, similar to Earth's Sargasso Sea but on a global scale, with mats of vegetation or colonial organisms forming drifting islands that provide shelter and food for a whole community of creatures. Yet, for all its raw power and visible drama, the surface is merely the skin of the planet, the thin interface between the immense, complex system of the deep ocean and the vastness of space. Everything that happens here is driven by forces from below and above. The heat from the deep currents influences surface temperatures, which in turn drive the winds. The chemistry of the deep ocean, rich with nutrients from geothermal vents, eventually upwells to the surface to fertilize the photosynthetic zones. The storms that rage on the surface are fueled by the heat stored in the upper ocean, which itself was warmed by the sun. Understanding this world requires seeing the surface not as a separate entity, but as the most visible and active part of a fully integrated system. It is the place where the internal energy of the planet meets the external energy of its star, and the resulting turbulence is what we see as weather, waves, and ice. This constant state of flux is the norm, not the exception. There is no calm, permanent state. There is only a continuous adjustment, a never-ending quest for equilibrium that is never quite achieved. For explorers, the surface would be the first and most formidable barrier. Landing a probe would mean surviving a descent through a thick, turbulent atmosphere and then an impact with a potentially raging sea. Once on the water, a vessel would have to be designed to withstand being pummeled by waves and tortured by winds, all while trying to collect data or dive beneath the chaos. The dynamic surface is both the gateway to this alien world and its most forceful guardian. a realm of breathtaking beauty and unimaginable power that defines the very character of a planet without land. But beneath that tumultuous surface, the ocean does not simply give way to uniform darkness. It organizes itself into a vertical universe of distinct layers, each with its own rules, its own chemistry, and its own potential for life. This entire depth, from the air-water interface down to the unimaginable bottom, is known as the water column, and it is anything but a homogeneous soup. It is a stratified stack of environments, a towering apartment building where the conditions on the top floor are radically different from those in the basement. And moving between them is like travelling to different worlds. The first and most familiar layer is the photic zone, the sunlit realm that extends down as far as light can penetrate. Here, sunlight drives the engine of photosynthesis, powering microscopic algae and other plant-like organisms that form the base of the food web for the entire planet. This is the bustling, energetic metropolis of the ocean, where life is abundant and fast-paced. Organisms here are adapted to float and drift, with structures to maximize their exposure to light and to avoid sinking into the darkness below. The water is warmer, mixed by wind and waves, and rich with oxygen produced by the photosynthetic activity. This is where you would find the great floating forests of algae, the shimmering schools of small creatures that feed on them, and the larger predators that hunt in the well-lit waters. But the sunlight does not last forever. As we descend, the blue light fades, and we enter the twilight zone, or the mesopelagic. This is a realm of perpetual gloom, where only the faintest traces of sunlight filter down. Not enough for photosynthesis, but just enough to create a world of shadows and silhouettes. The pressure here is already building, and the temperature drops significantly. Life in the twilight zone has adapted to this dim existence in remarkable ways. This is the kingdom of bioluminescence, where creatures create their own light through chemical reactions. They use these living headlights to hunt, to communicate, to attract mates, and to startle predators. Many animals here undertake a massive daily migration, travelling hundreds of meters up into the photic zone under the cover of night to feed, and then retreating to the relative safety of the dim depths during the day to avoid visual predators from above. This great vertical migration is one of the largest movements of biomass on the planet, and it acts like a biological elevator, constantly shuffling nutrients and energy between the surface and the deep. Below the twilight zone lies the aphotic zone, a place of absolute and eternal darkness. No sunlight reaches here at all. The pressure is now crushing, and the temperature is near freezing. This vast realm is further divided into the bathypelagic, abyssopelagic, and hadalpelagic zones, each deeper and more extreme than the last. In the aphotic zone, the primary source of energy is not the sun, but the slow, constant rain of organic debris from above, known as marine snow. This shower of dead cells, fecal matter, and other biological particles provides a meagre but vital food source for filter feeders and scavengers. Life here is sparse and must be highly efficient. Organisms often have slow metabolisms, grow very slowly, and can live for extraordinarily long times. They are adapted to the pressure, with flexible bodies that lack any air-filled spaces, and many are transparent or black to blend into the endless night. But there is another, more dramatic source of energy in the deep, geothermal power, on the seafloor, whether it is rocky or covered in hot ice. Hydrothermal vents can crack open, spewing superheated, mineral-rich water into the cold depths. These vents become oases of life, supporting dense communities based on chemosynthesis. Here, bacteria use the chemical energy from hydrogen sulfide or methane to produce organic matter, forming the base of a food web that includes giant tube worms, bizarre clams, blind shrimp, and many other specialized creatures. These ecosystems are entirely independent of sunlight, proving that life can thrive in the most isolated and extreme conditions. The Hadal Zone, the very deepest part of the ocean found in trenches or the deepest abyssal plains, is the most forbidding. The pressure here is thousands of times greater than at the surface, enough to crush most submarines. Yet, life persists even here, with organisms adapted to withstand these incredible forces, perhaps feeding on the scraps that drift down or on the bacterial mats that grow on the sea floor. The water column itself is not just a passive container. Its physical and chemical properties create barriers and highways for life. Sharp changes in temperature and salinity, called clines, can act as invisible walls, preventing species from moving between layers. For example, a creature adapted to the warm, sunlit surface would be killed by the cold and pressure of the deep, and a deep-sea organism brought to the surface would expand and perish. Conversely, the slow, vertical currents and the great animal migrations connect these zones, allowing for the exchange of nutrients and genetic material. The chemistry of the water changes with depth as well. Oxygen levels can become very low in certain mid-water zones, creating oxygen minimum zones where only specially adapted organisms can survive. The pH can vary, becoming more acidic with depth due to the accumulation of carbon dioxide from respiration and the decomposition of organic matter. This vertical stratification means that the biodiversity of a water world is not spread out horizontally, like across continents on Earth, but vertically, in a dense, layered cake of habitats. A single location on the map could host dozens of distinct ecosystems stacked on top of each other, from the photosynthetic producers at the top, through the migratory consumers in the middle, down to the chemosynthetic communities at the bottom, for any intelligent life that might evolve here. Their perception of the world would be profoundly vertical. Their maps would not be of coastlines and mountains, but of depth zones and current streams. Their concept of distance might be more about pressure changes than horizontal travel. Exploring this vertical universe is a monumental challenge. A submarine would need to be a master of buoyancy control, able to hover at specific depths to study each layer. Its instruments would have to function across a huge range of pressures and temperatures. To understand the planet, you cannot just skim the surface. You must undertake a grand descent, sampling each zone and understanding how they interact. The water column is the true heart of this world, a dynamic, living structure that defines everything from the global climate to the evolution of life. It is a universe in itself, waiting to be explored, one dark, mysterious layer at a time. The journey down through the water column is a journey through time and adaptation, revealing the incredible resilience of life and the vast, hidden complexity of a world that, from the outside, appears to be nothing but a featureless blue marble. This journey through the layered water column naturally leads us to wonder about the passengers on this vertical voyage, the life forms that have called this endless blue home for eons, and how their evolutionary story unfolds in a universe without any land. Evolution on a water world would follow a path utterly alien to our own, shaped by the relentless pressures of a fully aquatic existence where the very concept of a shoreline is a geological myth, without the selective pressures of terrestrial environments like beaches, marshes, or plains. The driving forces for change are concentrated entirely within the water column itself and on the mysterious ocean floor. The transition from simple to complex life would be governed by competition for resources in a three-dimensional arena, where every depth offers a different set of challenges and opportunities. The first major divergence from Earth's history is the complete absence of any impetus to leave the water. There are no drying ponds forcing fish to develop limbs, no tidal zones encouraging creatures to bask in the air, and no nutrient-rich coastal shelves beckoning for colonization. Instead, evolution is a story written in the language of buoyancy, pressure adaptation, and mastery of a fluid medium. The primary selective pressures would involve efficiency in movement through water, the ability to withstand crushing pressures or drastic temperature changes between layers, and strategies for finding food and mates in an environment where visibility is often zero and distances are measured in vertical meters rather than horizontal miles. Intelligence, as we understand it, might very well emerge in such a setting, but it would look nothing like our own. Imagine a species of highly social pelagic predators, roaming the open waters in vast pods. Their intelligence would not be geared towards manipulating dry objects or harnessing fire, but towards coordinating complex group hunts, navigating by sensing subtle changes in water pressure and chemistry, and communicating intricate information about prey locations and social status. Their society might be built around the defense of migratory routes or fertile hunting grounds defined by currents and upwellings, rather than territories on a static map. The development of technology, a hallmark of intelligent life on Earth, faces a fundamental barrier here. Fire is impossible underwater. This single fact reroutes the entire technological tree. There is no smelting of metals, no ceramics, no controlled combustion for energy. So, what replaces it? Tool use might evolve, but it would be based on biology and the manipulation of the environment itself. Creatures with dexterous appendages, like powerful tentacles or specialized fins, might learn to use natural objects, sharp rocks, hard shells, or even the bones of their prey as primitive tools for digging, breaking open hard-shelled food, or constructing simple shelters on the seafloor. But more advanced technology could involve the sophisticated manipulation of water itself. Intelligent beings might learn to harness currents, creating directed flows to herd prey or build structures from hardened bubbles of mucus or other secreted materials. They might cultivate bioluminescent bacteria to create reliable light sources or even use controlled electrical discharges for hunting or communication. The very definition of a tool expands to include the fluid medium they inhabit. Communication would be the cornerstone of any complex society in this world, and it would be far more advanced in acoustic and electroreceptive domains than in visual ones. In the dim light of the twilight zone or the absolute darkness of the abyss, vision is often useless. Instead, sound becomes the primary sense. Complex languages could develop based on clicks, whistles, and low-frequency rumbles that travel for miles in the dense water. These languages might convey not just simple alerts but intricate narratives, historical records, and abstract concepts. Bioluminescence would serve as a secondary, more localized communication system used for facial expressions, signaling in close-quarters social interactions, or even as a form of writing using patterned flashes. In some species, the ability to generate and interpret weak electric fields, like some earth fish, could evolve into a sophisticated private channel for communication, imperceptible to predators or prey. This would be a world where conversations happen in a symphony of sound and light, a rich sensory experience we can barely imagine. The evolutionary history of complex life would be a saga of adaptation to niches defined by the vertical dimension. Species would specialize not just in what they eat, but in the precise depth and pressure range they can tolerate. A creature might evolve to spend its entire life within a narrow 100-meter band of the water column, its physiology perfectly tuned to that specific pressure and temperature. This could lead to incredible biodiversity, with thousands of species occupying the same horizontal coordinates but separated by depth as effectively as if they were on different continents. The seafloor, or the hot ice crust, would host its own unique evolutionary pathways. Bottom-dwelling organisms might develop a more sedentary lifestyle, perhaps cultivating gardens of chemosynthetic bacteria or building elaborate, coral-like structures from minerals precipitated from hydrothermal vents. The competition for space on the seafloor could drive the evolution of territorial behaviours and complex construction abilities, but always within the constraints of an aquatic environment. The move from the seafloor into the water column itself would be a major evolutionary leap, analogous to animals moving from the ocean to land on Earth. But here it is a transition into a vast, open, three-dimensional space. Pelagic life forms would evolve streamlined bodies, sophisticated buoyancy control systems like swim bladders filled with fats or oils instead of air to avoid compression issues, and enhanced sensory systems to navigate the featureless blue. Predation strategies would be refined in this 3D arena. Ambush predators might hover motionless, camouflaged against the background light, while pursuit predators would evolve for speed and endurance in the open water. The social structures that emerge could be incredibly complex, with pods or schools functioning as superorganisms, making collective decisions about migration, hunting, and defense. The concept of family and community would be deeply tied to the group's ability to survive in a fluid and often hazardous environment. Without fixed landmarks, their navigation would rely on an innate sense of the planet's magnetic field, the position of celestial bodies filtered through the water's surface, or an acoustic map of the ocean floor topography. Their culture, their myths, and their very understanding of the universe would be rooted in the endless ocean. The sky above would be a distant, shimmering ceiling, its stars and sun distorted by waves, an object of curiosity but not a realm to be conquered. Their technology, if it advanced, would be biotechnology, growing tools and structures from living materials, harnessing microbial energy for power, and perhaps even genetically engineering themselves to adapt to new depths or changing ocean conditions. The path to something we would recognize as civilization would be long and twisted, following a logic born of water and pressure. It might never lead to radio telescopes or space travel, but it could result in a deeply sophisticated society that has mastered its aquatic world in ways we can only dream of. The evolution of life on a water world is a testament to the creativity of natural selection, proving that intelligence and complexity can flourish in the most unexpected places, following a blueprint written not in stone and fire, but in current and darkness. But the story of life in this aquatic realm is inextricably linked to the blanket of air that lies above it, an atmosphere that is both a product of and a partner to the global ocean beneath. The air on a water world would be profoundly shaped by the endless evaporation from its surface, creating a thick, humid shroud rich with water vapour, which is itself a powerful greenhouse gas. This constant cycling of water between the liquid ocean and the gaseous atmosphere creates an intimate feedback loop that dominates the planet's climate. The primary composition of the permanent gases, things like nitrogen, oxygen, and carbon dioxide, would not come from weathering rocks or volcanic outgassing from continents, as there are none, but would be almost entirely dictated by the biological and geochemical processes happening within the ocean itself. If photosynthetic life thrives in the sunlit surface waters, it would be pumping vast quantities of oxygen into the atmosphere, potentially creating an oxygen-rich environment similar to Earth's. Conversely, if life is mostly based in the deep, relying on chemosynthesis and producing gases like methane or hydrogen sulfide. The atmosphere might be a reducing one, filled with these compounds and lacking free oxygen. The balance of these gases is a delicate dance. Too much methane and you get a super greenhouse effect. Too much carbon dioxide and the ocean could become acidic, affecting the entire marine biosphere. The winds on such a planet would be a relentless force, blowing over a surface with no topographic features to create turbulence or disrupt their flow, without mountains or valleys to break them up. These winds could achieve remarkably high and consistent speeds, sweeping around the globe in broad, uniform bands. These persistent winds are the primary sculptors of the ocean's surface, whipping up those monumental waves and driving the surface currents that form the planet's circulatory system. The interaction between the wind and the water is so direct that energy is transferred with brutal efficiency, meaning storms can form quickly and persist for incredibly long times. The atmosphere also acts as the planet's temperature regulator. The thick layer of water vapor and other greenhouse gases traps heat that would otherwise radiate back into space, keeping the surface warm and liquid. This is why a water world can remain habitable over a wider range of distances from its star. The ocean and atmosphere work in tandem to buffer against temperature extremes. However, this balancing act is precarious. If the planet orbits too close to its star, the increased solar energy could trigger a runaway greenhouse effect. In this scenario, the rising temperature leads to more evaporation, which puts more water vapor into the air, which traps more heat, leading to even more evaporation. This positive feedback loop could eventually become unstoppable, heating the ocean until it literally boils away into space, leaving behind a desolate, steam-shrouded rock. On the other hand, if the planet is too far from its star, the opposite can happen. A slight cooling can increase ice formation at the poles, and because ice is highly reflective, it bounces more sunlight back into space, cooling the planet further and leading to a runaway glaciation that could encase the entire world in a global ice shell. The history of the planet's atmosphere is written in this struggle between heating and cooling, between the stabilizing influence of the ocean's heat capacity and the destabilizing potential of these feedback loops. The exchange of gases at the air-water interface is a constant, dynamic process. The ocean absorbs gases from the atmosphere, like carbon dioxide, which can then be used by marine organisms or become dissolved in the water, influencing its chemistry. In return, the ocean releases gases, most obviously water vapor, but also oxygen from photosynthesis or other trace gases from biological activity. This exchange means that the atmosphere is essentially a mirror reflecting the chemical state of the ocean. By analysing the atmosphere from a distance, using spectroscopy, we can infer the composition of the ocean and even guess at the kind of life that might exist there. For instance, the simultaneous detection of oxygen and a reducing gas like methane would be a powerful, though not definitive, biosignature, as these gases react quickly and their coexistence suggests a constant replenishment, likely from biological sources. The pressure at the surface would be higher than on Earth due to the dense, water-laden air, which could have interesting effects on any potential surface phenomena. Clouds would be a permanent and dominant feature, covering large swathes of the planet in a thick, swirling blanket. Precipitation would be constant in many regions, but with no land to run off onto, rain would simply fall back into the ocean, completing a short, local cycle. The sky's colour might be different too, with so much water vapour and perhaps other aerosols. It could appear whiter or have a permanent hazy quality. The day-night cycle would be softened by this thick blanket, with no sharp temperature drops after sunset, for any hypothetical intelligent life in the ocean. The atmosphere would be a distant, largely inaccessible realm. They might perceive it as a shimmering, distorted ceiling, its patterns of light and dark hinting at weather systems they could never experience directly. Their understanding of their universe would be based on the sounds and pressures that penetrate from above, like the low-frequency rumble of distant storms or the changes in surface wave action that filter down into the depths. From a human exploration standpoint, the atmosphere is our first point of contact and our key to studying the planet. A probe entering this atmosphere would face a thick, turbulent, and likely stormy environment. Parachutes might be less effective in the dense air, and the probe would have to be designed to handle intense humidity and possibly corrosive conditions if the atmosphere has unusual chemistry. Once through the atmosphere, the splashdown into the ocean would be the next great challenge. The atmosphere of a water world is not a separate entity. It is the ocean's voice, its breath, and its thermostat. It is a system in constant, dynamic equilibrium with the vast body of water below, each influencing the other in a complex planetary dance. Understanding this relationship is crucial to understanding the planet's past, its present, and its future potential for life. The climate stability over geological timescales depends on this ocean-atmosphere coupling, and it is this very stability that might allow life the time it needs to arise, evolve, and perhaps even look up from the waves to wonder about the shimmering sky. The study of such atmospheres is already underway with telescopes like the James Webb Space Telescope, which is analysing the light from distant exoplanets to decipher the composition of their air. Every new spectrum is a piece of the puzzle, helping us to understand the diversity of worlds in our galaxy and refining our search for those that might, like Earth, be alive. The atmosphere of a water world is a testament to the interconnectedness of planetary systems, where the sea and the sky are two parts of a single, inseparable whole. While the study of a water world's atmosphere from a distance provides invaluable clues, it is only through direct, in situ exploration that we can hope to confirm the presence of life, map the ocean floor, and understand the complex chemistry of the deep. Sending a robotic mission to such a planet represents one of the most formidable engineering challenges ever conceived, a multi-stage endeavour that pushes the boundaries of our current technology. The mission would logically be divided into two distinct phases: an orbital survey and a daring descent into the ocean itself. The first phase involves a sophisticated orbiter, a spacecraft designed to circle the planet for an extended period. Its primary job would be to conduct a global reconnaissance, using a suite of instruments to map the surface of the ocean in incredible detail. It would analyse wave patterns, monitor sea ice formation and retreat at the poles, and study the complex cloud formations and storm systems in the atmosphere. Spectrometers would dissect the light passing through the air, refining our understanding of its composition, while radar and LiDAR could potentially measure surface roughness and even infer shallow ocean currents. The orbiter's most critical task would be to identify the optimal entry point for the descent probe. Scientists would look for regions that might be particularly interesting, such as areas with unusual chemical signatures in the atmosphere suggesting possible biological activity, or locations where thermal scans indicate warmer surface waters or potential upwelling zones that could be rich in nutrients. This careful selection process is crucial because once the probe is committed to its descent, there is no going back. It must land in a spot that maximizes the scientific return of the entire mission. After the target zone is chosen, the second, much more dangerous phase begins. The descent probe, containing the submarine, must separate from the orbiter and begin its fiery plunge through the atmosphere. encased in a heat shield to protect it from the intense friction and heat of entry. The probe would streak across the sky like a meteor. The atmospheric entry is a violent and unpredictable process. The thick, humid air would create tremendous turbulence, and the probe would need a robust guidance system to maintain its trajectory and avoid tumbling. Parachutes or retro-rockets would then deploy to slow its descent for the final approach. The moment of impact with the ocean surface would be a massive shock. A jarring transition from the void of space to a violent, watery realm. The probe's shell would be designed to absorb this impact and then release the submarine, which must immediately begin its operation. This submarine is the heart of the mission, and its design is a nightmare of conflicting requirements. The first and perhaps most profound challenge is autonomy. The vast distance between this water world and Earth means that communication signals can take hours, or even days, to travel one way. Waiting for instructions from mission control for every decision is impossible. Therefore, the submarine must be incredibly smart, equipped with advanced artificial intelligence that allows it to operate independently for months or years. It needs to be able to navigate on its own, using sonar to map its surroundings and avoid obstacles like underwater ice formations or treacherous terrain. It must have the cognitive ability to recognize scientifically interesting features, a strange chemical gradient, a cluster of potential organisms, a hydrothermal vent plume, and decide to investigate them, altering its pre-programmed mission plan in real time. This level of autonomy is unprecedented in planetary exploration and requires software that is both highly sophisticated and extremely reliable. As a single software glitch could mean the loss of the entire mission, powering this intelligent vehicle for a long-duration mission is the next colossal obstacle. Solar energy is not an option once the submarine descends below the first few hundred meters, as sunlight is quickly absorbed by the water. Batteries could provide power for a short time, but they are too heavy and have insufficient energy density for a mission lasting years. The only realistic solution is a nuclear power source. A radioisotope thermoelectric generator, or RTG dot, is the leading candidate. It works by converting the heat released from the natural decay of a radioactive isotope, like plutonium-238, directly into electricity. RTGs are reliable, have no moving parts, and can provide a steady, low level of power for decades. However, they must be carefully shielded to prevent radiation from interfering with the submarine's sensitive instruments, and their use raises safety and political concerns during launch from Earth. The submarine would need to be designed to use this power with maximal efficiency, likely spending much of its time in a low-power sleep mode, only waking up fully to conduct experiments or move to a new location. Communication is another seemingly insurmountable hurdle. Radio waves, the standard for space communication, are effectively useless in water. They are absorbed within meters to send its precious data back to Earth. The submarine would need an alternative method. One concept involves using a low-frequency acoustic modem, essentially using sound waves to transmit data. However, sound travels slowly in water, and its path can be distorted by variations in temperature, pressure, and salinity, severely limiting the data rate and range. A more likely scenario is the use of disposable communication buoys. The submarine would carry several of these buoys and release them at predetermined intervals. The buoy would float to the surface, deploy an antenna, and then transmit the stored data at high speed to the orbiter, which acts as a relay station back to Earth. This method creates a logistical chain, where the submarine's data output is limited by the number of buoys it can carry. The physical design of the submarine is a study in extreme engineering. It must withstand pressures thousands of times greater than Earth's atmosphere at sea level. To do this, Its main hull would almost certainly be a perfect sphere or a series of spheres. As this shape distributes pressure evenly, the hull material would need to be incredibly strong yet lightweight. Titanium alloys are a possibility, but advanced composites or ceramics might be necessary. Every penetration in the hull for sensors, cameras, or manipulator arms is a potential point of failure, requiring ingenious sealing technologies. The outside of the submarine would be a hostile environment. The water could be highly corrosive if it is salty, or it might have an unusual pH that attacks metal. All external components would need to be made from corrosion-resistant materials or coated with protective layers. The submarine would need a propulsion system that is both powerful and energy efficient, likely using slow-turning propellers to navigate the dense water. It would require sophisticated ballast systems to control its buoyancy, allowing it to hover at a specific depth or make controlled ascents and descents. Its scientific payload would be a suite of miniaturized laboratories. Cameras with powerful LED or laser lights would be essential for imaging, but their range would be limited to a few tens of meters in the particle-filled water. Mass spectrometers would analyze the chemistry of the water, sniffing for organic molecules. Sensors would constantly monitor temperature, pressure, and salinity. A manipulator arm, capable of operating under immense pressure, would collect samples of water, sediment, or even biological material, since returning samples to Earth is likely impossible for such a mission. The submarine would need onboard labs to perform initial analyses, perhaps using microscopes to look for cells or instruments to sequence any discovered genetic material. The entire mission is a high-risk, high-reward endeavour of almost mythical proportions. It would require international cooperation, decades of development, and a budget of billions. But the potential payoff is equally monumental. The first definitive proof of life beyond our planet. A detailed map of an alien sea, and a revolutionary new understanding of how oceans and planets work. It is the ultimate robotic adventure, a journey into the deep unknown that would forever change our place in the universe. The immense technological hurdles of sending a probe into the abyss are driven by one burning question. Could such a world truly be teeming with life? The answer, surprisingly, might be found right here on Earth, in the most extreme and isolated parts of our own oceans. These earthly analogues provide a powerful blueprint for how a rich and complex biosphere could flourish on a planet covered entirely by water, suggesting that these worlds might be among the most life-friendly places in the universe. The most compelling analogue is undoubtedly the deep-sea hydrothermal vent ecosystem, discovered only in the late 20th century. These oases on the seafloor are completely divorced from the energy of the sun. Instead, they are powered by chemosynthesis, where specialized bacteria harness the chemical energy from superheated, mineral-rich water spewing from the Earth's crust. These bacteria form the base of a food web that supports astonishing densities of life, including giant tube worms that have no mouth or digestive system but host these bacteria symbiotically inside their bodies, bizarre blind shrimp that swarm around the vent mouths, and unique species of clams and crabs. The existence of these vibrant communities, thriving in total darkness under immense pressure, is a definitive proof of concept. It demonstrates that life does not need sunlight to prosper. It only needs a source of energy and a suite of key elements. On a water world, where geothermal heat from the planetary core would be a constant, global feature, such vent systems could be commonplace. Instead of being rare oases, they could form a planet-wide network of thriving ecosystems, each potentially hosting its own unique suite of organisms adapted to the local chemistry and flow rates. The scale of life could be staggering, with vast fields of vent-dependent creatures covering the seafloor or the hypothetical hot ice crust. But the deep vents are not the only analogue. The mesopelagic zone of Earth's oceans, often called the twilight zone, shows us how life adapts to a world of diminishing light. Here, in the perpetual gloom, bioluminescence is the dominant form of communication. Countless species of fish, jellyfish, and squid create their own light through chemical reactions, using it to attract mates, lure prey, startle predators, and camouflage themselves against the faint downwelling light from above. The profusion of flashing, glowing, and shimmering life in this zone paints a picture of how a water world's mid-depths could be a realm of constant, silent conversation written in light, on a planet with no land. This twilight zone could be immensely thick, creating a global habitat for bioluminescent organisms on a scale we can hardly imagine. The communication networks could be incredibly complex, with different species using specific flash patterns or colours, potentially even evolving towards a form of symbolic language based on light. The open ocean, or pelagic zone, of Earth provides another crucial piece of the puzzle. The vast schools of fish, from small anchovies to giant tuna, demonstrate the potential for a massive, mobile food web based on the productivity of the surface, on a water world. The entire surface would be a single, continuous photosynthetic engine, microscopic phytoplankton, drifting in the sunlit layer, would form the base of a planetary food chain. These would be grazed upon by zooplankton, which in turn would be consumed by larger and larger predators. Without continents to block migration, we could see the development of truly global migration routes, with immense herds of filter-feeding creatures or schools of predatory fish circumnavigating the planet, following the seasonal blooms of plankton and the shifts in ocean currents. The biomass supported by such a system could be astronomical, potentially far exceeding the total biomass of all life on land on Earth. The existence of these powerful analogues on Earth makes a strong case that ocean worlds are not just potentially habitable, but could be prime real estate for complex life in the cosmos. The continuous, three-dimensional nature of the habitat is key. On Earth, life is constrained by the two-dimensional surface of the land and the relatively thin layer of the productive ocean. On a water world, the entire volume of the ocean, from the surface down to the abyssal plains, is a potential home. This creates a staggering amount of living space, with countless niches defined by depth, pressure, temperature, and chemistry. This vertical dimensionality could drive speciation to an extreme degree. Organisms could become hyper-specialized for life within a very narrow band of the water column, leading to a biodiversity that dwarfs our own planets. We might find creatures that never leave the warm surface waters, others that spend their entire lives in the cold, high-pressure darkness of the abyss, and still others that undertake daily vertical migrations of kilometers, experiencing drastic changes in pressure and temperature as a normal part of their life cycle. The implications for the evolution of intelligence are profound. In such a vast, interconnected, yet layered world, the selective pressures for complex communication, navigation, and social cooperation would be immense. We could envision the rise of intelligent, social predators in the open ocean, coordinating hunts across vast distances using sound and bioluminescence. Or we might find sophisticated tool users on the seafloor, manipulating minerals and cultivating chemosynthetic bacteria in vent fields. The path to technology would be utterly alien, bypassing fire and metallurgy in favour of bioengineering, pressure manipulation, and acoustic or chemical computing. The very continuity of the habitat means that genetic and cultural exchange could occur on a global scale, potentially leading to a single, planet-wide biological network, a global superorganism in a way that is impossible on a fractured world like Earth. This notion of a richer biosphere is not just speculation. It is a logical extension of the principles we observe in Earth's oceans, just amplified to a planetary scale. The sheer volume of the environment, the constant recycling of nutrients by global currents, and the multiple, independent energy sources from both sunlight and planetary heat create a recipe for an incredibly fertile world. When we imagine sending a probe into such an environment, we are not just hoping to find a few extremophile microbes clinging to existence. We are entertaining the very real possibility of diving into a teeming, bustling, and bewilderingly diverse living ocean. A world where life has filled every conceivable niche from the sun-dappled surface to the crushing, dark depths. The challenges of exploration are monumental, but the potential reward is the discovery of a second genesis of life, and with it, the profound understanding that we are not alone in a silent universe, but merely one expression of a cosmic imperative towards complexity and consciousness in the vast, dark seas of space. The Earth's analogues are our guide, showing us that the conditions for life are not narrow and fragile, but robust and adaptable, ready to flourish wherever liquid water and an energy source persist. This realization transforms our view of the cosmos, suggesting that the silent, blue marbles we see orbiting distant stars may not be barren wastelands, but the most vibrant and alive worlds of all. But if life can indeed flourish in such abundance, the next logical and thrilling question is whether that life could ever gaze up at the shimmering ceiling of its world and wonder about its place in the cosmos, developing intelligence and perhaps even a civilization. Detecting such intelligence, however, would be a challenge unlike any other, because every aspect of their existence would be fundamentally shaped by the liquid medium that surrounds them. Imagine an intelligent species that evolved not on land, but in the open water, a pelagic creature with a complex social structure necessary for hunting and defense in the vast, featureless blue. Their intelligence would be molded by the need to navigate in 3 dimensions, to communicate over long distances without light, and to solve problems without the fundamental tool that propelled our own technological ascent: fire. Fire is impossible underwater, and that single fact completely reroutes the entire technological tree of any aquatic civilization. There is no smelting of metals, no forging of tools, no controlled combustion for energy or propulsion. So what replaces it? Their path to technology would have to be based on entirely different principles. Perhaps the manipulation of pressure, the harnessing of chemical energy from geothermal vents, or the sophisticated use of biology itself. Tool use might still develop, but it would look nothing like our hammers and knives. Creatures with dexterous appendages might learn to use sharp rocks or hard shells as primitive tools. But more advanced technology could involve the cultivation of living materials. They might learn to grow structures from coral-like organisms, engineer bacteria to perform specific tasks, or manipulate bubbles of gas for buoyancy or even as primitive lenses. Their entire material science would be based on biotics and the clever use of what the ocean provides, leading to tools and machines that are grown, not built. Communication is another area where the aquatic environment dictates entirely different rules. For us, radio waves are the backbone of long-distance communication and technology, but radio waves are useless in water. They are absorbed within meters. For an intelligent species in the ocean, sound would be the equivalent of our radio. Sound travels far and well in water. and a sophisticated civilization would likely develop complex languages based on clicks, whistles, and low-frequency rumbles that can carry for hundreds of miles. These languages could convey not just simple alerts but intricate information, stories, history, and abstract concepts. Beyond sound, bioluminescence could serve as a form of close-range visual communication, perhaps for art or social bonding, and some species might even evolve to use electroreception, generating and interpreting weak electric fields for private, short-range messaging that predators cannot overhear. The very concept of a city or a home would be transformed. Without solid ground, structures cannot be built from stone and mortar. Instead, habitats might be grown from biological materials, vast living reefs cultivated for shelter, or clever use might be made of natural formations. They might learn to trap pockets of air or other gases within flexible membranes to create buoyant structures that float at a specific depth. Or they might anchor their communities to the seafloor near reliable sources of energy like hydrothermal vents. Their entire society would be organized around the vertical dimension and the constant flow of currents, with transportation networks following invisible highways in the water rather than roads on land. The development of science and astronomy would face unique hurdles. For us, looking up at the stars was a primal step towards understanding the universe. For them, the sky is a distorted, shimmering ceiling, its images blurred and broken by waves. Seeing the stars clearly would be tremendously difficult, though not necessarily impossible. A truly curious species might learn to breach the surface, or even develop lenses that can correct for the distortion, but their view of the cosmos would always be filtered through the ocean's surface. This might delay their understanding of orbital mechanics or the scale of the universe, or it might lead them to discover physics through other means, perhaps through the study of fluid dynamics or the subtle gravitational pulls that create tides. So, how would we, from our distant vantage point on Earth, ever detect such a civilization? We cannot listen for their radio signals, as they would not use them. We cannot look for city lights on the surface, as their cities would be in the depths. Instead, we would have to look for more subtle technological signatures, or techno-signatures. One promising avenue is the atmosphere, a global industrial civilization, even an aquatic one, would likely alter the chemistry of its planet's atmosphere in detectable ways. Just as our burning of fossil fuels has filled our air with greenhouse gases, their activities might release unusual combinations of gases that are hard to explain through natural processes alone. For example, the large-scale cultivation of certain biological organisms or industrial-scale chemistry driven by geothermal power could produce complex synthetic compounds that leave a specific spectroscopic fingerprint. We might also look for evidence of large-scale energy use. If they are harnessing geothermal energy on a massive scale, it might create a thermal anomaly detectable as an unusual heat signature on the night side of the planet. Alternatively, if they use nuclear fission or fusion, there might be associated radioactive isotopes or neutrinos that could, in theory, be detected, though this is far beyond our current capabilities. Another possibility is looking for evidence of planetary engineering. A civilization aware of climate change might attempt to geoengineer their world, perhaps by releasing particles into the atmosphere to control temperature or by managing the ocean's chemistry on a global scale. Such large-scale interventions could create an atmospheric composition that is wildly out of equilibrium with what would be expected for a natural water world. We might also consider the possibility of detecting their artifacts indirectly. While we cannot see their structures, if they are large enough, they might influence global ocean currents in a detectable way, or create artificial structures on the seafloor that somehow affect the planet's rotation or gravitational field in a minuscule but measurable way. The most haunting possibility is that we might detect their communications, but not recognize them as such. The complex acoustic signals they use for conversation and data transmission would, to our instruments, simply sound like natural ocean noise, the songs of whales, the cracking of ice, the rumble of currents. It would take a sophisticated analysis to distinguish an intelligent language from the background chorus of the planet. We would need algorithms designed to identify complex patterns, syntax, dot seam, and information density in the acoustic data. A monumental task requiring immense computational power and a deep understanding of what constitutes communication in a medium so alien to us. The search for intelligence in a water world is therefore a search for subtlety and context. It requires us to expand our definition of technology and to look for signs that defy natural explanation without jumping to conclusions. It is a humbling endeavour, one that reminds us that our way of building a civilization is just one path among many potential ones. The universe might be filled with intelligent beings who have never looked at the stars, but who have mastered the depths of their aquatic homes, communicating in songs of sound and light, their history and culture flowing as endlessly as the currents that carry them. Finding them would not only tell us that we are not alone, but it would fundamentally reshape our understanding of what life and intelligence can be. While the search for intelligence focuses on the water column, the ultimate foundation of this entire world, both literally and figuratively, is the ocean floor, a landscape of dramatic topography and powerful geothermal energy that would shape the planet's chemistry and potential for life in profound ways. The absence of continents does not mean a flat, boring seabed. Far from it. Without the constant grinding and crumpling of plate tectonics as we know it, the ocean floor might be a more static, but still incredibly varied, panorama. Imagine vast, sprawling abyssal plains, flatter than any desert on Earth, stretching for thousands of miles, covered in a thick, fine sediment that has settled from the water above over billions of years. These plains would be punctuated by colossal mountain ranges, volcanic seamounts that rise from the depths like submerged islands, some peaking thousands of meters from the seafloor but still remaining far beneath the ocean's surface. These underwater mountains would create their own localized currents and ecosystems, acting as oases of hard substrate in a world of soft sediment. Then there would be the trenches, chasms deeper than the Mariana Trench, plunging down into the ultimate darkness where pressures reach their astronomical maximum. These trenches might be rare if plate tectonics are subdued, but they could still exist as scars from the planet's violent early history. The topography of the seafloor is the stage upon which the deep ocean's drama plays out, directing the slow, cold bottom currents that flow like underwater rivers, channeling nutrients and oxygen to the deep sea communities, and creating barriers that can isolate populations and drive evolution. The most critical features on this seafloor, however, are not the passive mountains and plains, but the active, energy-releasing vents that connect the ocean to the planet's fiery interior. Hydrothermal vents, often called black smokers, are chimneys formed from minerals that precipitate out of superheated water gushing from beneath the seafloor. This water has been heated to extreme temperatures by magma, leaching minerals from the surrounding rock until it is a rich, chemical soup. When this 350 degrees Celsius fluid erupts into the near-freezing deep ocean, the minerals instantly solidify, building towering structures that can be as tall as skyscrapers. These vents are more than just geological curiosities. They are potential cradles of life. On Earth, they support entirely independent ecosystems based on chemosynthesis. where bacteria convert the toxic hydrogen sulfide and other chemicals into energy. In the perpetual darkness of a water world, these vents would be beacons of energy, likely the primary centres for any complex deep-sea life. The entire planet might be dotted with these vents, forming a global network of biological hotspots. But the vents are not the only show in town. Cold seeps are another crucial feature, places where fluids saturated with methane and hydrogen sulfide slowly percolate up through the sediment on the seafloor. Unlike the violent, focused flow of hydrothermal vents, seeps are often slower and more diffuse, creating vast mats of bacteria that break down the chemicals. These bacterial mats form the base of a food web that can include tube worms, clams, and other specialised organisms. On a water world, where the primary source of new nutrients from land erosion is zero, these seeps and vents become the planet's lungs and kidneys, recycling chemicals from the mantle and providing the essential building blocks for life. Methane, in particular, could be a key molecule. Vast reservoirs of methane hydrate, an ice-like solid that forms under high pressure and low temperature, could be stored in the seafloor sediments, if released, perhaps by an underwater landslide or a shift in temperature. This methane could erupt powerfully, both providing a sudden feast for methanotrophic bacteria and potentially altering the ocean's chemistry and even the atmosphere above if the bubbles reach the surface. The seafloor would also be the site of persistent, if not constant, volcanic activity. Submarine volcanoes would dot the landscape, their eruptions dramatically different from those on land. The immense water pressure would suppress explosive eruptions, leading instead to the slow extrusion of lava, forming vast pillow lava fields that look like piles of giant stone pillows. This volcanic activity is the primary engine of the planet's long-term geochemistry. It constantly adds new material to the crust, releases volatile gases into the ocean, and provides the heat that drives the hydrothermal systems. The rate of this volcanic activity is a key factor in the planet's habitability. Too little, and the ocean becomes a stagnant, nutrient-poor desert. Too much, and the water could become toxic with volcanic gases. The interaction between the water and the hot rock also drives the circulation of water through the crust in a process called hydrothermal circulation. Seawater seeps down into cracks in the seafloor, is heated by the underlying magma, becomes buoyant, and rises back up, laden with dissolved minerals. This global plumbing system is a massive chemical reactor, slowly but constantly altering the composition of the ocean, removing some elements and adding others. It is through this process that vital nutrients like iron, phosphorus, and sulfur are continuously injected into the deep ocean, from where they can be carried by currents to fertilize the rest of the world. The topography of the seafloor directly influences these life-giving processes. A mountain range can deflect a deep current, creating a nutrient-rich upwelling on one side and a barren shadow on the other. A trench can act as a sediment trap, accumulating organic material and creating a unique, food-rich environment for scavengers and detritus feeders. The slopes of a seamount can accelerate currents, funneling plankton and other food particles towards filter-feeding communities that cling to the hard rock. For any explorer, mapping this hidden landscape would be a priority. Using side-scan sonar from an orbiting spacecraft or a deep-diving submarine, we could chart the major features, the plains, the ridges, the seamounts, and the trenches. But the real prizes, the vents and seeps, would be much harder to find. They would be identified by their chemical and thermal signatures, a sudden spike in temperature or a cloud of suspended minerals in the water, detectable by sensitive instruments on a robotic submarine. The discovery of a vent field on an alien water world would be an epoch-making event. We would look for the telltale signs of life, the dense communities of organisms, the microbial mats, the strange, mineralized structures. The life there might be vaguely familiar, following the same chemosynthetic principles as on Earth, or it could be radically different, using alternative biochemical pathways we have never seen. The seafloor, in its silent, dark, and pressurized grandeur, is the true heart of this planet. It is the source of the energy and nutrients that could sustain a global biosphere, the sculptor of the deep currents, and the keeper of the planet's geological history. It is a world within a world, a hidden landscape of immense scale and profound importance, waiting in the darkness for the first glimmer of a light from a visiting submarine, a light that would reveal wonders beyond our wildest imagination. Understanding this foundation is key to understanding everything about the water world that lies above it. Building on the idea of the sea floor as a dynamic source of chemical richness, we must now explore how those raw materials become the building blocks for life, cycling through the ocean in a complex dance that sustains any potential biosphere on a world without continents. The very concept of a nutrient cycle is turned on its head. There is no erosion from land to wash phosphorus, iron, and other vital elements into the sea. Instead, the primary source of these nutrients must come from within the planet itself, through the relentless geothermal activity on the ocean floor. Hydrothermal vents and cold seeps act as the planet's lifelines, constantly injecting a soup of dissolved minerals and gases into the deep water. This chemical broth includes essential elements like iron, sulfur, manganese, and even trace metals that are crucial for enzymatic reactions in living organisms. Without this continuous geological replenishment, the ocean would slowly become depleted of the elements needed to build and power life, turning into a barren, clear blue desert over geological time. The cycle of these nutrients then depends entirely on the physical and biological processes that move them around the global ocean. The first step is their distribution from the point of source. The slow, deep currents that flow along the seafloor act as colossal conveyor belts, picking up these dissolved nutrients from the vent systems and carrying them across the abyssal plains. This creates vast, invisible rivers of fertility flowing through the darkness. However, for life in the sunlit surface layers to benefit, these deep nutrients must somehow travel upwards. This is where the global circulation pattern, the thermohaline conveyor, becomes the planet's heart. In regions where deep water is forced to the surface, a process known as upwelling, these nutrient-rich waters are brought into the photic zone. Upwelling is often driven by wind patterns pushing surface water away, allowing deeper water to rise and replace it, on a planet with no land. These upwelling zones could be widespread and persistent, creating permanent areas of high biological productivity similar to Earth's richest fishing grounds. Here, in the sunlit surface, the nutrients finally meet the energy of sunlight. Phytoplankton, microscopic photosynthetic organisms, eagerly absorb these nutrients, using them to grow and multiply. This explosion of primary production forms the base of the entire food web for the upper ocean. Zooplankton graze on the phytoplankton. Small fish eat the zooplankton, and larger predators hunt the smaller fish, creating a complex pyramid of life that depends entirely on that initial upwelling of deep nutrients. But the cycle does not end there. A critical part of the nutrient loop is the downward journey. Waste products, dead cells, and other organic debris from the surface communities slowly sink through the water column in a constant, gentle rain, known as marine snow. This organic snowfall is a vital source of food for filter feeding and scavenging organisms in the deep sea. More importantly, as this material sinks, it is decomposed by bacteria, a process that releases the nutrients back into the water in inorganic forms, making them available again for uptake. This creates a biological pump, actively transporting carbon and nutrients from the surface to the deep. The efficiency of this pump determines how much carbon is sequestered in the deep ocean and how quickly nutrients are recycled. On a water world, this pump could be incredibly efficient due to the immense depth and the lack of shallow coastal areas where decomposition happens quickly. The daily vertical migration of millions of organisms adds another layer to this cycle. Countless animals, from tiny crustaceans to larger fish, undertake a massive journey each day, rising to the surface waters at night to feed and descending to the depths during the day to hide from visual predators. This immense movement acts as a biological elevator, actively transporting nutrients in their bodies. When they excrete waste at depth, they are effectively fertilizing the deep ocean with nutrients captured from the surface. Similarly, when they die and sink, they contribute to the marine snow. This daily migration could be a dominant mechanism for vertical nutrient transport on a world where physical upwelling might be limited in some regions. The availability of specific nutrients can become the limiting factor for life across the entire planet. On Earth, nitrogen and phosphorus are often the elements that control the growth of algae. In a water world, phosphorus might be particularly scarce because its main source on Earth is the weathering of continental rocks. Without that source, the entire biosphere might be phosphorus limited, meaning that the total biomass the planet can support is capped by the slow rate at which phosphorus is released from volcanic seafloor rocks or delivered by the rare asteroid. Iron is another critical nutrient, especially for photosynthetic organisms, and its solubility in seawater is low. On Earth, iron is often delivered by dust blown from deserts. On a water world, that atmospheric source is absent, so iron must come entirely from seafloor vents and seeps. The distribution of life would therefore be tightly linked to the distribution of these geothermal nutrient sources and the currents that carry their products. The chemistry of the water itself plays a role in the nutrient cycle. The pH, temperature, and salinity affect how easily nutrients dissolve and remain available for organisms. For instance, in a more acidic ocean, certain essential minerals might precipitate out of solution, becoming inaccessible. The constant mixing by currents helps to homogenize these conditions, but sharp gradients, like the thermocline where temperature changes rapidly with depth, can act as barriers, trapping nutrients in specific layers. The cycle of carbon is particularly important and is intimately tied to the nutrient cycles. Carbon dioxide from the atmosphere dissolves into the surface ocean, where phytoplankton use it for photosynthesis. When these organisms die and sink, they carry carbon with them to the deep. Some of this carbon is used by deep sea life, and some is buried in sediments on the seafloor, effectively removing it from the atmosphere for long periods. This process helps regulate the planet's climate by drawing down greenhouse gases. On a water world, the carbonate-silicate cycle that stabilizes Earth's climate is absent, so this biological carbon pump becomes one of the primary climate regulators. The long-term stability of the climate and the biosphere are therefore dependent on the balance of this nutrient and carbon cycling. If something disrupts the flow, if volcanic activity slows and nutrient input drops, or if the ocean circulation stagnates, the entire system could collapse into a state of low productivity. Conversely, an increase in geothermal activity could flood the ocean with nutrients, potentially causing massive algal blooms that could deplete oxygen in some areas when the algae die and decompose. For any intelligent species that might evolve, understanding these cycles would be fundamental to their survival. Their migration routes, their cultural practices, and even their myths would be shaped by the seasonal pulses of nutrient upwelling and the great migrations of prey species. They might develop a deep intuitive or even scientific understanding of oceanography long before they ever conceive of a world beyond the water. For us, as external observers, detecting the signature of an active nutrient cycle could be a key step in identifying a living world. An atmosphere with seasonal fluctuations in oxygen or certain biomarkers could indicate a biosphere that is breathing, powered by the constant rise and fall of nutrients in a global ocean. The nutrient cycle is the silent, endless rhythm of a water world, the process that transforms a sterile chemical soup into a thriving, living planet. It connects the fiery depths of the sea floor to the sun-dappled surface, and every organism, from the smallest bacterium to the largest predator, is a passenger on this great biochemical carousel, considering the intricate nutrient cycles that could support a vibrant alien biosphere. The idea of humans one day establishing a home on such a water world shifts the perspective from observation to survival, pushing the boundaries of human endurance and innovation in ways that challenge every aspect of our existence. The challenges would be existential, fundamentally testing our engineering, biology, and social structures in realms we have only begun to explore through science fiction and speculative research. Unlike the native life forms evolved for these conditions over millions of years, humans would be fragile intruders in an environment where every basic need, air, water, food, and shelter, must be artificially provided against a backdrop of crushing pressure, eternal darkness, and profound isolation that defies terrestrial experiences. The first and most immediate concern is habitat design, which must address the relentless force of the deep ocean. Living underwater requires structures that can withstand immense pressures, especially at any meaningful depth beyond the first few 100 meters where the weight of the water column becomes astronomical. These habitats would likely be designed as spheres or cylinders, shapes that distribute pressure evenly to prevent collapse, much like the concepts proposed for deep-sea research stations on Earth, but scaled for permanent residence. Made from advanced materials like titanium alloys, carbon composites, or even transparent ceramics for viewports. These pressurized modules would need to be perfectly sealed and rigorously tested to withstand pressures thousands of times greater than atmospheric pressure at sea level. They could be anchored to high points on the seafloor, such as seamounts or volcanic ridges, to provide stability and access to geothermal energy sources for power and heat, leveraging the planet's internal warmth to reduce reliance on external energy. Alternatively, they might be designed to float at specific depths using controlled ballast systems, allowing them to remain in the photic zone for solar power or in warmer layers to minimize energy consumption for temperature regulation. Each habitat would function as a self-contained life support system, recycling air and water with meticulous precision to sustain human life indefinitely. Carbon dioxide scrubbers would remove exhaled carbon dioxide, while electrolysis or plant-based systems would replenish oxygen, creating a balanced atmosphere within. Water would be recycled from waste and humidity through advanced purification processes to prevent contamination by microbes or chemicals, ensuring a safe supply for drinking and hygiene. The loss of pressure integrity would mean instant catastrophe, so redundant systems and rigorous maintenance schedules would be non-negotiable, with automated sensors constantly monitoring for leaks or structural fatigue to trigger immediate repairs. Beyond the engineering marvels, daily life inside these habitats would be characterized by claustrophobia and monotony, with limited personal space and a constant background hum of machinery that becomes the soundtrack of existence. Personal quarters would be compact and multifunctional, while communal areas would serve as dining halls, recreation spaces, and workstations to maximize efficiency in a confined environment. Agriculture on a water world could not rely on traditional soil-based farming. Instead, it would revolve around intensive aquaculture and algaculture integrated into the habitat infrastructure. Large underwater farms would cultivate fast-growing seaweed and algae, which serve a dual purpose, providing essential nutrition and aiding in oxygen production through photosynthesis under artificial lighting. These operations would require significant energy, potentially sourced from nuclear reactors or ocean thermal energy conversion systems that harness temperature differences between surface and deep water. Fish and other marine species could be farmed in enclosed pens, offering a reliable protein source. But this demands careful management to avoid disease outbreaks and pollution from accumulated waste. The entire food production system would operate as a closed loop, where waste from humans and animals is processed to fertilize the algae and plankton, mimicking natural cycles but on a tightly controlled, human-managed scale. This bioregenerative approach is crucial for long-term sustainability, as importing food from Earth would be impractical due to the vast interstellar distances and prohibitive costs. However, this system results in diets that are repetitive and heavily based on seafood and algae-derived products, with few familiar fruits or vegetables unless grown in specialized hydroponic modules that use nutrient solutions instead of soil, adding variety but requiring additional resources. Society in such an environment would necessarily be highly cooperative and structured around severe resource limitations, fostering a culture of shared responsibility and minimal waste. With no room for conflict or inefficiency, communities would likely evolve into tight-knit groups living in isolated arcs that function as independent units. These underwater cities might consist of multiple interconnected modules, forming a network that shares resources, expertise, and emergency support to enhance resilience. Governance would emphasize collective decision-making and strict rationing of energy, water, and food, possibly through a democratic or council-based system where every member has a voice in critical matters. The limited capacity of each habitat means populations would be small, perhaps a few hundred to 1,000 people per unit, leading to a distributed civilization across the ocean with minimal central authority and localized adaptations. Social roles would be clearly defined, with everyone contributing to essential tasks such as maintenance, agriculture, or research. And education would focus on practical skills necessary for survival, from engineering and medicine to marine biology and psychology. The isolation could foster innovation as communities develop unique solutions to local challenges, but it could also create cultural drift between different ARC communities, potentially leading to diverse micro-societies over time with distinct customs, languages, and social norms. Communication between habitats would rely on acoustic modems or fiber optic cables, enabling data exchange but with significant delays over long distances that could slow coordination and foster misunderstandings, necessitating robust protocols for conflict resolution and information sharing. The psychological impact on humans would be profound and multifaceted, affecting mental health in ways that require proactive management. Confined to artificial environments without natural horizons, people might experience sensory deprivation, claustrophobia, and a phenomenon akin to ocean madness, where the endless blue outside induces anxiety, depression, or existential crises. The lack of natural day-night cycles in the deep could disrupt circadian rhythms, requiring artificial lighting systems to simulate daytime and nighttime and regulate sleep patterns for overall well-being. The constant dependency on technology for survival could lead to heightened anxiety or a pervasive sense of vulnerability, with every system failure posing a life-threatening risk that amplifies stress levels. Mental health support would be crucial, with trained counselors and virtual reality technologies offering escapes to simulated terrestrial landscapes or social interactions to alleviate monotony and isolation. Community bonding activities, such as shared meals, games, and artistic endeavours, would help mitigate loneliness and stress, but the absence of open skies and the ever-present surrounding water could inspire both awe and existential dread, reshaping human consciousness and spiritual beliefs in ways we can barely imagine. Insights from Earth-based analogues like Antarctic research stations or nuclear submarines indicate that isolation and confinement can lead to crew tensions and psychological fatigue, underscoring the need for careful selection, training, and ongoing support for colonists to maintain cohesion and morale. Transportation between habitats would depend on advanced submarines, which would serve as the vital lifelines of this underwater civilization, enabling mobility and connectivity across the vast ocean. These vessels would need to be robust, capable of withstanding dramatic pressure changes, and energy efficient to navigate long distances without frequent refueling, relying on propulsion systems such as electric motors or possibly fusion power in the future for sustained operation. They would navigate using sonar and inertial guidance systems, as global positioning system signals are useless underwater, requiring precise mapping of the seafloor to avoid hazards. Cargo submarines would transport essential goods like food, materials, and people, creating a logistics network that connects the Ark cities and facilitates trade and cultural exchange. Maintenance and repair of these vessels would be a critical industry, conducted in pressurized dry docks within larger habitats, and any breakdown could isolate communities for extended periods, highlighting the importance of reliability and spare parts inventories. The design of submarines might evolve to include passenger comforts for long journeys, such as sleeping quarters and recreation areas, but travel would still be slow and risky due to potential mechanical failures or encounters with extreme weather at the surface, where storms could generate massive waves that pose additional dangers during ascent or descent. This transportation web would define trade routes and social interaction patterns, with some habitats specializing in manufacturing or research and others in agriculture, all interdependent for survival and prosperity. In conclusion, human adaptation to a water world would be a testament to our ingenuity and resilience, demonstrating an ability to overcome extreme environments through technology and cooperation. But it would come at a great cost in terms of personal freedom, psychological well-being, and resource constraints. The technological hurdles are immense, requiring advances in materials science, life support, and energy production that we are only beginning to develop, with each innovation needing to be foolproof to prevent disaster. Socially and psychologically, we would need to reinvent our ways of living, prioritizing collective action and mental health in an inherently hostile setting that offers no second chances. While the dream of colonizing the oceans might seem like science fiction, it forces us to confront the limits of our biology and the potential for human civilization to thrive beyond Earth, inspiring new approaches to sustainability and community on our own planet. Yet, such a life would always be precarious, a delicate bubble of air in an infinite sea, reminding us of the fragility of our existence and the beauty of the world we left behind, and perhaps teaching us valuable lessons about humility and adaptation in the face of the unknown. The profound challenges of adapting to life in a submerged habitat force a deeper, more fundamental question about our very perception of reality. Because the discovery of a world without any land at all would not just be a scientific curiosity, it would be a philosophical and cultural earthquake that rattles the core of human self-perception. Our entire history, our mythology, and our very sense of identity are inextricably tied to the land. From the biblical "be fruitful and multiply" and fill the earth and subdue it to the age of exploration and the conquest of new continents, our narrative is one of foundation, exploration, and conquest of solid ground. A planet that is nothing but ocean challenges these foundational stories at their root. There is nothing to subdue, no new continents to plant a flag upon, no promised land flowing with milk and honey, only an endless, fluid, and ultimately unconquerable expanse. This forces a radical re-evaluation of what it means to explore, to settle, and to belong for humanity. It would underscore a humbling truth that our terrestrial experience is not the universal norm, but a very specific, perhaps even rare, condition in the cosmos. This realization would likely trigger a period of intense cultural and philosophical introspection, forcing us to confront our own anthropocentrism. Our art, our literature, and our music would be flooded with themes of fluidity, impermanence, and depth, contrasting sharply with our traditional themes of stability, roots, and solid horizons. The very concept of landscape would be redefined. For us, a landscape implies mountains, valleys, forests, and rivers, features with permanence and solidity. On a water world, the landscape is the seascape, a dynamic, ever-changing vista of waves, currents, and light. There is no permanent feature to orient oneself by, no mountain that has stood for millions of years. The only constants are change and flow. This would fundamentally alter the human sense of place and time. Our psychology is built around landmarks. Without them, our navigation and our very memory of place would have to adapt. For a native intelligence evolving on such a world, their entire perception of reality would be built around this fluidity. Their myths of creation would not involve a god separating the land from the water, because there was only ever water. Their foundational stories might involve a great current that brought life, or a deep, dark abyss from which the first beings emerged. Their concept of the divine would likely be vast, deep, and immersive, rather than a sky father residing in a high place. Their idea of nature would not be a separate entity to be visited or conquered, but the total, all-encompassing medium of their existence. There would be no concept of wilderness as a place apart from civilization, because everything is the same, continuous wilderness. This could foster a worldview that is inherently more integrated and less adversarial than our own historical relationship with nature. For humans attempting to live there, the psychological impact would be profound. The absence of a horizon line, a fundamental visual anchor for our species, could be deeply disorienting. On the open ocean, the horizon is a flat line separating two blues. Under the water, there is no horizon at all, just a gradual fading of light into blue, then green, then black in every direction. This lack of a visual boundary can induce feelings of agoraphobia and a terrifying sense of exposure. Or its opposite, a claustrophobic sense of being trapped in an infinite, featureless prison. The human mind craves pattern and reference, and the homogeneous nature of the water column could deprive it of that, leading to unique forms of psychological stress that we are only beginning to understand from studies in sensory deprivation tanks and long-duration spaceflight. The relationship with water itself would be transformed from something we visit, something we cross, or something we drink, into something we are immersed in every moment. It is the walls of your home, the road you travel, the source of your food, and your greatest threat. This intimate, total dependency would likely foster a culture of deep respect and caution, but also one of incredible adaptability. Human cultures on Earth that live closely with the sea, like various Polynesian and Austronesian peoples, have developed sophisticated navigational skills and a deep spiritual connection to the ocean. On a water world, this would be amplified to a planetary scale. The culture would likely centre on themes of community, cooperation, and resilience in the face of a powerful and indifferent environment. The value of individualism, so prominent in many terrestrial societies built on owning and conquering land, might be supplanted by an emphasis on collective survival. Your neighbour is not just someone who shares a fence line. They are someone who shares the same fragile bubble of air, whose survival is directly linked to your own. This could lead to highly structured, cooperative societies with strong social bonds, but it could also create intense pressure to conform. The very idea of property would be revolutionized. Without land, the concept of owning a piece of the planet becomes absurd. Instead, property might be defined by access rights to specific water columns for aquaculture, or mining rights to hydrothermal vent fields on the seafloor. Wealth would not be measured in acres, but in knowledge, technology, and control over vital resources like energy, fresh water, and food production capacity. The history and culture of such a human society would be vertical, not horizontal. Their maps would be three-dimensional charts of currents, thermoclines, and nutrient-rich upwelling zones. Their heroes would be not conquerors of land, but master navigators who discovered new current streams, or engineers who designed more efficient habitat life support systems. Their exploration would be a descent into the abyss, a journey inward into pressure and darkness, rather than an outward expansion across a surface. This inward turn could make them deeply introspective as a culture, more concerned with understanding the intricate workings of their own world than with looking outward to the stars. For them, the ultimate frontier is not space, but the Hadal zone at the bottom of their ocean, the discovery of a water world, and any attempt to live on one holds up a mirror to our own culture. It forces us to see how much of what we consider universal human nature is actually just a product of our specific planetary environment. It challenges our narratives of dominance and control and suggests that a successful future for humanity, even on Earth, may depend less on conquering nature and more on learning to flow with it, to adapt to its rhythms, and to recognize our profound interdependence with the systems that sustain us. The philosophical implications are vast, pointing towards a more humble, adaptive, and integrated view of intelligence in the cosmos, where success is measured not by the ability to dominate the environment, but by the wisdom to live in harmony with it. This world without land is not just an alien planet. It is a challenge to the very foundation of the human story, asking us who we are when the ground literally vanishes from beneath our feet. The profound shift in human perspective, from land-based conquerors to fluid integrated inhabitants, naturally forces a complete overhaul of our economic principles, moving from a model of extraction and accumulation to one of integration and cyclical sustainability. On a world without any solid ground, the very definition of a resource is transformed. There are no forests to cut down, no mines to dig, no oil fields to drill. Instead, the entire economy must be built upon what the global ocean provides, which is almost entirely biological or dissolved within the water itself. This means that the most basic economic activities, like mining for minerals, become exercises in large-scale filtration and chemical processing. The water itself is a liquid mine, containing trace amounts of virtually every element. but in such dilute concentrations that extracting them requires immense amounts of energy and sophisticated technology. Imagine massive offshore platforms not for oil, but for pumping vast quantities of seawater through series of filters and ion exchange resins to capture valuable metals like lithium, uranium, or even gold. The efficiency of this process would dictate the entire technological base of the society. If it is too energy intensive, only the most critical elements would be extracted, severely limiting industrial development. Alternatively, the more lucrative and concentrated mineral deposits would be found at hydrothermal vents on the seafloor. These geological features are natural smelters, constantly spewing out rich plumes of metal sulfides that precipitate into towering chimneys of copper, zinc, silver, dot, and other ores. Mining these vents would be a dangerous and technologically daunting task, requiring autonomous robots or heavily reinforced manned vehicles that can operate under crushing pressures and near boiling temperatures. The environmental impact would be a primary concern, as these vents are also likely oases of life, and their destruction could collapse entire deep-sea ecosystems that the planet's biosphere depends on. Therefore, the economy would have to balance the need for raw materials with the absolute imperative of preserving these fragile, life-giving systems. This leads to the second pillar of the water world economy: energy. With no fossil fuels and limited access to solar energy for anything submerged below the first 100 meters, the inhabitants would turn to the ocean's own dynamic forces. The most promising source is likely ocean thermal energy conversion, which harnesses the temperature difference between the warm surface waters and the cold, deep waters to drive a heat engine and generate electricity. This would require massive infrastructure, with long, cold water intake pipes stretching down into the abyss and large surface platforms, but it could provide a constant, baseline power source. Another significant source would be the kinetic energy of the currents. The planet-girdling currents we discussed earlier are immense reservoirs of energy, and underwater turbines, similar to wind turbines but designed for water's density, could be deployed in strategic corridors to generate power. In regions with high volcanic activity on the seafloor, geothermal energy could be tapped directly, using the planet's internal heat to create steam or power Stirling engines. The distribution of this energy would define economic zones. Areas with strong, reliable currents or sharp thermal gradients would become the industrial heartlands, while calmer regions might be reserved for other purposes. However, the greatest economic asset, the true currency of this world, would not be mineral or energy, but biological. The sheer biodiversity of a global ocean, especially if it hosts alien life, represents an unimaginable treasure trove of biochemical innovation. Every organism, from the smallest microbe to the largest predator, is a library of genetic code that has evolved over billions of years to solve problems of survival under extreme conditions. The potential for discovering new pharmaceuticals is staggering. Enzymes from pressure-resistant bacteria could lead to new industrial catalysts that work under high pressure and temperature. Antifreeze proteins from organisms living under the ice caps could revolutionize cryogenics. Novel antibiotics, painkillers, or even cognitive enhancers could be derived from the chemical defenses and communication systems of the native fauna. This bioprospecting would be the primary driver of scientific research and a major export if contact with other human colonies existed. The economy would therefore value biologists, chemists, and geneticists as highly as we value software engineers or financiers today. The management of this biological wealth leads to the third and most critical economic principle: radical sustainability. A water world is essentially a closed system There is no away to throw pollution. Any waste produced circulates globally and eventually comes back to haunt you. A toxic spill from a mining operation at one vent site could be carried by currents to poison ecosystems thousands of miles away. Overfishing a particular species could collapse a food web that spans the entire planet. Therefore, the entire economic system must be designed as a circular economy from the ground up. Every product must be designed for disassembly and recycling. Waste would be seen not as garbage, but as a resource out of place. Organic waste would be composted and used to fertilize algaculture farms. Metallic waste would be meticulously sorted and fed back into the extraction facilities. The concept of planned obsolescence would be economically suicidal and socially unacceptable. This necessitates a high degree of regulation and monitoring, likely enforced by a global or regional governing body that has the authority to impose strict quotas and environmental standards. This brings us to the final, and perhaps most culturally disruptive, economic shift. The redefinition of property. Without land, the idea of owning a piece of the planet becomes meaningless. You cannot own the water, you can only use it. Therefore, economic rights would be based on usage and stewardship. A community or corporation might be granted exclusive rights to a specific three-dimensional volume of the ocean, a water column, for a set period, with the obligation to manage it sustainably. This could be for aquaculture, where they farm fish or kelp, or for mining a specific hydrothermal vent field. These rights would not be permanent. They would be contingent on meeting environmental performance metrics. Similarly, hunting rights for migratory species would be allocated, not to individuals, but to collectives who must ensure the long-term health of the population. This system prioritizes access over ownership and responsibility over exploitation. It fosters a long-term perspective that is often missing in terrestrial economies. The accumulation of personal wealth would look very different. There would be no vast estates or private islands. Wealth might be stored in the form of energy credits, data, especially genetic data, or shares in sustainable aquaculture or energy operations. The most valuable individuals would be those with the knowledge to maintain and advance the complex, closed-loop systems that keep everyone alive. In this economy, the ultimate luxury might not be a bigger house, but a private submarine for exploration, or a larger allocation of energy for personal projects. The daily life of an average person would be deeply integrated into this economic model. Most jobs would revolve around the maintenance of life support systems, food production, resource recycling, and scientific research. Education would focus on ecology, engineering, and systems management from a very young age. The economy is not something separate from society. It is the practical manifestation of the cultural values of fluidity, adaptation, and community that we discussed earlier. It is an economy built not on conquering nature, but on learning to dance with its endless, powerful rhythms, understanding that in a world of water, the only constant is flow, and the only true capital is the health of the global ocean that sustains you. This economic model, while born of necessity, could serve as a powerful blueprint for sustainable living on any planet, reminding us that prosperity does not require endless growth, but can be found in balance, intelligence, and a deep respect for the systems that give us life. Imagine a world where the oceans stretch to the horizon in every direction, a concept that once lived only in the pages of science fiction novels and the frames of cinematic adventures. Today, that very idea has leaped from fantasy into the realm of scientific inquiry, as astronomers and researchers have begun to confirm the existence of planets entirely covered by water, transforming our understanding of the cosmos. The story of this discovery is a fascinating journey that mirrors the evolution of human curiosity and technological prowess, starting with visionary writers who dreamed of alien seas long before we had the tools to find them. In the early 20th century, authors like Arthur C. Clarke and later filmmakers depicted worlds with global oceans, sparking public imagination and inspiring generations of scientists. These fictional portrayals, while speculative, laid the groundwork for the scientific community to consider the possibility of such environments, pushing the boundaries of what we thought was possible in planetary formation. However, it wasn't until the late 20th and early 21st centuries that technology caught up with imagination. Thanks to advancements in space telescopes and detection methods, the launch of missions like the Kepler Space Telescope marked a turning point, allowing scientists to survey thousands of stars for signs of orbiting planets. By observing the subtle dimming of starlight as a planet transits its host star, researchers could infer the planet's size and, combined with mass measurements from other techniques, calculate its density. It was this method that revealed the first hints of water worlds, exoplanets with densities too low to be purely rocky, suggesting they were composed largely of lighter materials, with water being a prime candidate. For instance, planets in the TRAPPIST-1 system or others like K218b showed characteristics that pointed to significant water content, either as vast surface oceans or thick ice layers. This shift from speculation to data-driven discovery was propelled by international collaboration and the development of more sophisticated instruments, such as the Hubble Space Telescope and later the James Webb Space Telescope, which can analyze the atmospheres of these distant worlds. Spectroscopy became a key tool, as it allows scientists to dissect the light passing through a planet's atmosphere, identifying chemical signatures like water vapor, methane, DOT, or oxygen that could indicate habitability or even biological activity. The confirmation of water worlds isn't just about finding water. It's about redefining the habitable zone and challenging our Earth-centric views of life. Early definitions of habitability were narrow, focused on planets similar to our own, but the discovery of these ocean planets has expanded that view, showing that life could thrive in environments once deemed too extreme. This historical journey from fiction to fact also highlights the importance of interdisciplinary work, where astrobiologists, planetary scientists, and astronomers come together to interpret the data. Moreover, the role of public engagement and education cannot be overstated, as science fiction continues to inspire real-world missions and research priorities. As we look to the future, proposed missions like those to Europa or Enceladus, icy moons with subsurface oceans, serve as stepping stones to understanding full water worlds, demonstrating how fictional ideas have become central to modern space exploration. The history of discovering water worlds is thus a testament to human ingenuity, showing that our dreams often pave the way for discovery, and that the universe is far more diverse and wondrous than we ever imagined. The transition from imaginative stories to hard scientific evidence didn't happen overnight. It was a gradual process fueled by both technological innovation and a shifting cultural mindset. In the 1960s and 70s, science fiction television shows and movies often featured aquatic aliens and water-covered planets, embedding the concept in popular culture and making it a staple of speculative thought. These narratives, while entertaining, also posed serious questions about the nature of life and the conditions required for its existence. Questions that scientists began to take more seriously as our understanding of planetary science evolved. The first major step toward confirmation came with the discovery of exoplanets in the 1990s, which shattered the assumption that our solar system was the standard model for planetary systems. Pioneering work with radial velocity measurements revealed gas giants orbiting other stars. But it was the transit method that eventually uncovered smaller, potentially watery worlds. The Kepler mission, launched in 2009, was a game changer, designed specifically to find Earth-sized planets in or near the habitable zone. Over its operational lifetime, Kepler identified thousands of candidate planets, and among them were those with densities suggesting they were not rocky like Earth but had significant volatile components, including water. Researchers used follow-up observations from ground-based telescopes and other space observatories to refine these findings, leading to the identification of several promising water world candidates. For example, Dotjol, the planet GJ1214b, discovered in 2009, was one of the first where models indicated a substantial water layer, possibly a global ocean under a thick steam atmosphere. Similarly, the TRAPPIST-1 system, with its 7 Earth-sized planets, includes several that might have large amounts of water, based on density calculations and atmospheric studies. The James Webb Space Telescope, with its advanced infrared capabilities, is now taking this research further by probing the atmospheres of these planets for water vapor and other gases, providing direct evidence of their composition. This ability to characterize atmospheres is crucial because it helps distinguish between a water world with a thick steam atmosphere and one with a clear ocean surface, each with different implications for habitability. The scientific community's acceptance of water worlds as a real class of planets has also been influenced by theoretical models of planetary formation. Scientists now understand that planets can form in the colder outer regions of protoplanetary disks, where ice is abundant, and then migrate inward, bringing their water with them. Alternatively, they might acquire water later through comet impacts, a process that could lead to oceans covering the entire surface if the planet lacks significant land masses. This theoretical framework, combined with observational data, has turned what was once a fringe idea into a mainstream topic in astrobiology. The history of this discovery is also a story of collaboration across borders, with researchers from different countries sharing data and resources to achieve common goals. Missions like the European Space Agency's CHEOPS and NASA's TESS have built on Kepler's legacy, finding more water world candidates and refining our understanding of their properties. Public interest has remained high, driven by media coverage and educational outreach, which helps secure funding for future missions. The journey from science fiction to scientific confirmation has not only expanded our knowledge of the universe, but also inspired new generations to pursue careers in science and engineering. It shows how creativity and rigor can work together to uncover truths about our place in the cosmos. As we continue to explore, the legacy of those early imaginative stories remains, reminding us that the line between fantasy and reality is often thinner than we think, and that the next great discovery might be waiting in the depths of an alien ocean. But as we shift from marveling at the discovery of these worlds to the practical reality of exploring them, we are immediately faced with a profound ethical dilemma that could define our legacy as a spacefaring species. The very act of sending a probe to a potentially habitable water world carries the risk of irreversible contamination, where earthly microbes hitchhiking on our spacecraft could be introduced into that pristine alien ecosystem. Imagine a single, resilient bacterium from Earth surviving the journey and finding itself in a nutrient-rich alien ocean. It could multiply uncontrollably, outcompeting native organisms or disrupting delicate biochemical cycles we do not yet understand. This event, known as forward contamination, is not just a theoretical concern but a potential catastrophe that could erase the very evidence of alien life we seek or trigger an ecological collapse before we even have a chance to study it. The consequences are unpredictable. An introduced microbe might be harmless, or it could act as an invasive species, devouring local resources or producing waste products that poison the environment. This risk is amplified on a water world because liquids are excellent mediums for spreading life, and a global ocean means contamination could eventually circulate planet-wide, leaving no refuge untouched. The design and sterilization of any probe destined for such a world would therefore need to be impeccable, going far beyond the protocols used for Mars rovers. Current methods involve baking components at high temperatures and using harsh chemicals. But for a mission that must survive entry into an ocean, every seal, every joint, and every external sensor would need to be free of biological material to an unprecedented degree. However, achieving absolute sterility is practically impossible. We can only reduce the bioload to an acceptable risk level, which sparks debate on what acceptable truly means when dealing with an entire alien biosphere. This leads directly to the imperative of preservation. If we were to detect signs of native life, our approach must shift from mere observation to a form of cosmic stewardship. The principle of non-interference becomes paramount, requiring that we study this life without altering its environment or behaviour. This is akin to an anthropologist observing an uncontacted tribe from a distance, respecting their autonomy and avoiding any influence that could distort their natural development. For a water world, this might mean that our submarines and sensors are designed to be as passive as possible, avoiding direct contact with organisms or their habitats. We might rely on remote sensing, DNA sequencers that do not require sample extraction, or cameras that observe from a distance without disturbing the local chemistry. The goal would be to gather data without leaving a trace, treating the entire ocean as a protected wilderness area. This ethos of preservation is not just about scientific purity. It is a moral stance acknowledging that this world has its own intrinsic value, independent of its utility to humans. It raises questions about our right to interfere, especially if we discover complex or even intelligent life. The ethical debates here are intense and multifaceted. If we find a primitive microbial community, do we have the right to collect samples, even if it means destroying some individuals in the process? What if we encounter something more advanced, like a complex multicellular organism or a sentient being? The discovery of intelligence in a water world would force us to confront issues of rights and personhood in a context utterly alien to our own. Our historical track record on Earth, with colonialism and the exploitation of indigenous cultures, serves as a cautionary tale. We would need to establish guidelines for communication, interaction, and perhaps even coexistence that prioritize the well-being of the native life forms over our desire for knowledge or resources. This extends to the economic interests we discussed earlier. If a water world holds valuable biological compounds or minerals, the temptation to exploit it commercially could be immense. However, ethical exploration would demand that any economic activity be subordinate to preservation, allowing only non-invasive practices like observing and learning from the ecosystem without extraction. The existing framework for planetary protection, primarily developed for Mars and other dry bodies, would require drastic expansion and adaptation for aquatic environments. Current guidelines from organisations like COSPAR focus on preventing contamination by setting strict cleanliness standards for spacecraft. But a water world introduces new challenges. For instance, how do we sterilize a submarine that must operate in a liquid medium, where microbes could be released through water intake valves or from the hull itself? The protocols would need to cover not just the launch and landing phases, but the entire operational life of the probe in the ocean. This might involve developing new technologies, such as self-sterilizing materials that release antimicrobial agents or systems that isolate the probe's internal environment from the external water. Moreover, the definition of special regions, areas where Earth life might replicate, would need to be global for a water world, meaning the entire planet might be treated as one giant special region requiring the highest level of protection. This could make missions prohibitively expensive and complex, but the alternative, risking the destruction of a unique biosphere, is deemed unacceptable by many in the scientific community. The ethical considerations also touch on the very purpose of exploration. Is our goal to expand human presence, to seek resources, or to satisfy scientific curiosity? For a water world, the precautionary principle should guide our actions. When an activity raises threats of harm to the environment, precautionary measures should be taken even if some cause and effect relationships are not fully established. This means that in the face of uncertainty, we should err on the side of caution, prioritizing the protection of the alien environment over immediate scientific gain. For example, if a probe detects ambiguous signs of life, it might be programmed to avoid further investigation in that area to prevent potential contamination, even if it means missing a groundbreaking discovery. This conservative approach requires international agreement and enforcement, as a single mission from a non-compliant entity could jeopardize the entire ecosystem. The debate over the rights of any discovered life is particularly thorny. If we find intelligent beings, questions of moral consideration arise. Would they have rights to their planet, their culture, their way of life? Our anthropocentric views might not apply. Their intelligence could be so different from ours that we fail to recognize it, or their values might be incomprehensible to us. This calls for a broader, more inclusive ethical framework that respects other forms of consciousness and existence. Practical steps for ethical exploration include designing missions with built-in safeguards, such as abort mechanisms that can isolate the probe if contamination is detected, or communication systems that allow for remote shutdown if necessary. Education and public awareness are also crucial. By fostering a global understanding of the value of these alien worlds, we can build support for stringent protection measures. The future of water-world exploration depends on our ability to balance our innate curiosity with a deep sense of responsibility. It is a test of our maturity as a species, challenging us to look beyond our own interests and consider the well-being of other potential life forms in the cosmos. By embracing these ethical principles, we can ensure that our journey into the depths of alien oceans is one of respect and wonder, not conquest and exploitation, leaving a legacy of stewardship that honors the fragility and beauty of life wherever it may be found. The decisions we make today will set a precedent for all future interstellar exploration, defining how humanity interacts with the universe and its inhabitants for generations to come. The ethical framework we build today will be the foundation for the next great leap in exploration. A future brimming with ambitious missions and cutting-edge technology designed to finally answer the question of whether life exists in the alien oceans of distant worlds. This future is not a distant dream. It is taking shape right now in laboratories and space agencies around the globe, driven by a collective desire to probe the depths of these water worlds. The immediate next steps rely heavily on the powerful telescopes we have already placed in space and those being developed. The James Webb Space Telescope is currently leading this charge, using its unparalleled infrared capabilities to analyze the atmospheres of promising exoplanet candidates. By studying the starlight that filters through a planet's atmosphere, scientists can identify the chemical fingerprints of water vapor, methane, oxygen, and other potential biosignatures. This remote sensing is our first real look into the conditions on these worlds, helping us prioritize which ones warrant a closer, more invasive look. But Webb is just the beginning. Future observatories, like the planned Habitable Worlds Observatory, will be designed specifically to directly image Earth-like planets, allowing us to see them as more than just dots and to study their surface and atmospheric properties in far greater detail. These telescopes will help us create a shortlist of the most promising water worlds, those with not just water, but with atmospheric compositions that suggest geological activity or even biological processes. The data from these orbital eyes will be crucial for planning the next phase of exploration, sending probes to these distant systems, while interstellar travel remains a monumental challenge for the foreseeable future. Our own solar system offers a testing ground that is incredibly valuable. Icy moons like Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are considered miniature water worlds with vast subsurface oceans hidden beneath their frozen crusts. Proposed missions to these moons are the logical stepping stones to exploring exoplanets. For Europa, the Europa Clipper mission is set to conduct detailed reconnaissance, mapping its ice shell and probing the ocean below to understand its depth and composition. The next logical step after an orbiter is a lander, and eventually, a cryobot. A cryobot is a specialized probe designed to melt through the icy crust, potentially kilometers thick, to reach the liquid ocean beneath. It would be a nuclear-powered thermal drill, carrying a small submarine, or hydrobot, to explore the alien sea. The technological hurdles are immense. The cryobot must navigate through unknown ice structures, avoid getting trapped, and maintain sterility to prevent contamination of the potentially habitable environment below. Once through the ice, the hydrobot would be released into the darkness, becoming the first human-made device to explore an extraterrestrial ocean. It would need to be fully autonomous, equipped with sonar for navigation, cameras and lights for imaging, and a suite of sensors to analyze the water chemistry and search for signs of life. Similarly, for Enceladus, which actively vents its ocean material into space through geysers at its south pole, a simpler mission could fly through these plumes and analyze the samples directly. This eliminates the need to drill through ice, making it a very attractive target for a search for life. The lessons learned from exploring Europa and Enceladus will be directly applicable to the design of missions for true exoplanetary water worlds. The ultimate dream is an interstellar probe, but that requires propulsion technologies we do not yet possess. Concepts like laser sails, which use powerful lasers to push lightweight probes to a fraction of the speed of light, are being studied. But such a mission is likely decades away. For now, the focus is on developing the robotic explorers that could one day swim in those distant seas. The key technologies that need advancement are autonomy, communication, and power. A submarine on an alien world cannot be joysticked from Earth. The communication delay would be years. It must be smart enough to make its own decisions in real time, navigating treacherous terrain, identifying interesting scientific targets, and managing its own power and safety. Artificial intelligence for space robotics is a field of intense research, aiming to create systems that can operate independently for years. Communication is another nightmare. Radio waves do not travel well through water. So a submarine would need to use acoustic modems or release data buoys to the surface to relay information to an orbiting spacecraft. Power is the third great challenge. Solar power is useless in the deep ocean, and batteries have limited lifespan. The only viable option for a long-duration mission is a nuclear power source. like a radioisotope thermoelectric generator, which provides a steady, reliable trickle of electricity for decades. The physical design of the submarine itself must withstand pressures that could crush most metals, and it must be built from corrosion-resistant materials to survive in what could be a salty or chemically exotic ocean. The international collaboration required for such missions cannot be overstated. No single nation can bear the cost and risk alone. The success of missions like the James Webb Telescope, a partnership between NASA, the European Space Agency, and the Canadian Space Agency, shows the way forward. Exploring water worlds will require a global effort, pooling resources, expertise, and funding. This collaboration extends to the ethical guidelines we discussed. The world must agree on planetary protection protocols to ensure our exploration does not harm these pristine environments. The scientific payoff of these missions is potentially the greatest in human history: the discovery of life beyond Earth. Even finding simple microbes in the ocean of Europa or Enceladus would revolutionize our understanding of biology and our place in the universe. It would prove that life is not a fluke of Earth, but a common process in the cosmos. Finding complex life or even intelligence on an exoplanet water world would be an epoch-making event, fundamentally altering human philosophy, religion, and culture. The economic and technological spin-offs from this research are also significant. The challenge of building a submarine for an alien ocean will drive innovations in materials science, robotics, and energy production that will benefit us on Earth. The search for life forces us to push the boundaries of what is possible, inspiring new generations of scientists and engineers. The future of waterworld research is a journey of gradual steps, each building on the last. It begins with telescopes characterizing atmospheres from light years away, continues with probes to our neighboring icy moons, and culminates, one day, in submarines diving into the dark, deep oceans of planets orbiting other stars. It is a patient, persistent, and profoundly collaborative endeavor, driven by one of the most ancient human impulses: curiosity. The quest to find life in a water world is more than a scientific mission. It is a story we are writing about our own species, a testament to our ingenuity and our enduring hope that we are not alone in the vast, dark silence of space. Every new telescope launched, every mission proposed, brings us closer to the day when we might finally receive an answer, a signal from the deep that changes everything.